Hi friends, welcome to Gate Academy. Our next chapter is next or last thing that we are going to discuss in this quick revision session is design of flexural members. In design of flexural members, beams, built-up beams, there are purlins, grids, and everything. But majorly the problems flexural members means bending members. So you'll be using the flexure formula m by I equals to f by y equals to e by r. The major thing, if you're talking about design, you are going to calculate z required. M is the moment that is being applied upon that, and sigma cbc is permissible bending compressive stress. It is generally 0.66 times Fy in WSM, and in LSM it is Fy upon 1.1. And there are two types of things in this: laterally supported beam and laterally unsupported beam. If compression flange of the beam is completely restrained against the thing is, if it can't buckle like this, then it is laterally supported beam. If it can buckle like this, then it is a laterally unsupported beam. So permissible compressive stress is taken as 0.66 times Fy, and this is Fy upon 1.1. This is laterally unsupported beam, and that is laterally supported beam. Fine. Next, in buckling of the flange, in order to reduce this, B upon TF should not be more than 16, and B upon TF actually, if you remember, it should not be more than 16. In LSM, it should not be more than 8.4. We have already discussed that. So next problem is buckling of web. So buckling of the web, whenever if you see, there is possibility of buckling of the web. The major problems here is web buckling, web crippling. You have to design for web buckling and web crippling. So buckling of the web, which will be generally due to the diagonal compressive stress. Webs are always designed for shear forces, and flanges are designed for the flexural forces. So if I take the web, it is generally designed for the shear force due to the diagonal compressive stress. Because of the shear force, there will be diagonal tension and diagonal compression. Due to this diagonal compression, there will be web buckling. So in order to avoid that, we generally provide stiffeners, vertical stiffeners, horizontal stiffeners, and all those things. That is web buckling. And web crippling, under the huge amount of the load or under the supports, just below that flange, there will be buckling of the web. That is called as a web crippling. Local buckling of the web or web crippling or web crimpling. It is developed due to excessive bearing stress. Fine. So this is what you will generally see. Fine. And to prevent load buckling or load crippling, web buckling or web crippling, that is local buckling of the web. Let us say under the load, you'll take a dispersion line of 30 degrees, that is in WSM, whereas in LSM you'll take 1 in 10 2.5. 1 in 2.5 you'll take that in LSM. Fine. And this is H2 plus T. H2 plus T. Fine. If this is H2, where T is the thickness of the web, H is the depth of root fillet. If I take this as the H2 plus T, and this is alpha. Alpha would be equals to, if you take this is A, alpha would be A plus, if this is H2 plus T, just take tan 30 degrees or tan 60 degrees, you will get these values. If it is 1 in 2.5, you can take 1 in 2.5 and get the value of alpha, and see calculated bearing stresses is equals to load applied reaction or load applied upon effective bearing area of toe fillet. Bearing area would be this alpha multiplied with thickness of the web. Alpha would be equals to, load dispersion is important here. Here it is 30 degrees, and in LSM it would be, if you see, this is the load dispersion, that is 30 degrees here. In LSM, this would be 1 in 2.5. For a depth of 1, there will be this 2.5. This is 30 means this is 60 degrees. You are getting it? So if this is H2 plus T, this is 2.5 times H2 plus T. Just find out the alpha value. If it is under the load, you'll calculate like this, and if it is under the reaction, you'll calculate alpha something like this. This is this A plus this value, A plus that value, that is load dispersion line. Fine. So R or load upon bearing area of the toe of fillet, alpha multiplied with TW. Fine. So alpha equals to A plus X. You know how to calculate that X. So to prevent load buckling or load crippling, under the load, P upon alpha multiplied with TW, it should be less than 0.75 times Fy. So that means it is strong in bearing. There will not be any load buckling or web crippling. Next, web crippling or local buckling of web. In order to prevent web buckling, what you have to do is, if this is the load dispersion line, 45 degrees in WSM, 1 in 2.5 in LSM. So alpha value would be equals to A plus, if this is D2 plus T, D by 2. Now it would be D by 2. Buckling will be taken exactly at the center of the web, whereas web crippling will be taken near to the support or under the load. Fine. So just alpha value will change. Alpha value would be equals to A plus D by 2 plus T, where in previous case it is root 3 times H2 plus T, or 2.5 times H2 plus T. So length of imaginary column of effective length D by 2, you'll just calculate L upon R minimum. Fine. So alpha is the length, T is the thickness, R minimum is something like this, TW upon 2 root 3. From this you'll calculate lambda. Once you know lambda, a table will be given to you, you'll calculate sigma AC. So safe load carrying capacity, if it is less than applied load, then web buckling will not occur. Idea is to prevent web buckling and web crippling. In order to prevent web crippling, we have seen, in order to prevent web buckling, this is how you'll be taking. You'll just assume this as an imaginary column of length alpha, thickness T. You'll calculate R minimum, width alpha and thickness T, and length equals to D by 2. Fine. So just same thing. Alpha you'll calculate, R minimum you'll calculate. Just alpha here it would be A plus this plus this. If it is at the support, it is A plus D by 2 plus T. If it is over here, A plus 2 times D by 2 plus T. Fine. So these are the points that you should generally consider, and that is how you are going to design. So idea is to design for web buckling and web crippling in the beam. So these are the major things. There are plate girders, gantry girders and other things, but right now we are not much worried about it, because from gate point of view it is not important. So with this, your revision is completed. In the revision, I have discussed in detail about plastic analysis, because there is short question for it, and rest of the things I have given a basic idea, so that if a question is given to you, can solve. If majorly, if question is not given, you don't have to worry about it much. Fine. So don't waste your time, and all the best for your gate examination. Okay. Next concept is design of compression member. Fine. So design of compression members. We have seen a design of struts and everything. Design of compression members means fixing the sizes of the compression members and finding out the spacing between that. So what exactly you are going to do that? First of all, you have to assume the value of sigma AC. Fine. Generally sigma AC will be in the range of 60 to 80 MPa. For built up section, you have to assume 110 to 120 MPa. For normal sections, you will be assuming 60 to 80, and for built up sections, we will be assuming from 110 to 120 MPa. Fine. So after that, once you find out sigma AC, find out gross area required, that is load applied upon sigma AC. Once you find out the gross area, just fix out the area that you have to provide. Fine. Suitable sections, find sigma A and find lambda and sigma AC. Once you find out lambda and sigma AC, once again cross check it. The safe load carrying capacity should be more than load applied. Then design is safe. Fine. This is one of the things. Next, design of built up columns. Design of built up columns. In design of built up columns, the major thing that we'll be seeing is providing the spacing. Like instead of one channel sections, you are providing two channel sections, and spacing between the two channel sections is 2s. Sir, how exactly you are going to provide the spacing? Spacing should be provided in such a way that Ixx equals to Iyy. Why sir? Why? Because generally for each channel section, Ixx for individual sections, Ixx is far more than Iyy. Okay, is far more than Iyy. Small yy if I take, Ixx is far more than Iyy. I small xx is far more than I small yy. Okay, this is one of the thing. And finally, how you are going to design? You have to find out the spacing in such a way that Iyy for total thing, if you want to calculate, if I take this as Cxx, I capital Yy, I capital YY equals to I small YY plus CXX square multiplied with A. Area of each channel section multiplied with 2. This is IYY. This IYY should be equals to IXX. This is not CXX actually. If I have to say, this is CXX and this would be S spacing, and this is also S. Total spacing is 2S. Fine. So S plus CXX whole square. IYY plus S plus CXX whole square multiplied with A, that is equals to I capital XX. That is equals to I capital XS. I small capital YY equals to I small YY plus A multiplied with S plus CXX whole square, that equals to I capital XX. This is one of the important thing that you have to remember. Fine. So you have to design in such a way that S spacing is something like this. Then you can provide the spacing. Let me check whether mic is on or not. Yeah, mic is on. So this is how you're going to provide the spacings. Fine. And whatever the lambda should be less than equal to 180 for compression members. Once if you provide the spacings, after providing the spacing, the next important thing is design of lacings. Once you provide the spacings, yeah, there are 2 channel sections and these 2 channel sections have to be connected by the members. Now comes the lacings and battenings. For built-up members, if you see the plan, this is a channel section, this is a channel section, this is lacing, this is a lacing. On both sides, you will be going to provide the lacings. So design of lacings and battenings. Difference between lacings and battenings is lacing is an inclined member, whereas battening is an horizontal member. Lacing is an inclined member and battening is an horizontal member. So designing. If you talk about the designing, what should be the length? What should be the angle? What should be the width? What should be the thickness? And how much load you are going to design for this? And what is the spacing? That is how you are going to design it. Fine. So if you say this is the lacing, this is the lacing. Generally, lacing members are designed as truss members. Truss members means axial members. It takes only axial forces, either tension or compression. Lacing members are designed as truss members, that is they are subjected to either tension or compression only. Bending moment is 0 in the lacing member. Fine. And maximum slenderness ratio for lacing member is limited to 145. Slenderness ratio for the lacing member, that means this C upon R minimum should not be more than 145. Spacing between the lacings, C upon R minimum should not be more than 145. Sorry. L upon R minimum, L1 upon R minimum should not be more than 145. Angle between the lacing should be in the range of 40 degrees to 70 degrees. That is one of the important thing. Fine. So angle should be in the range of 40 degrees to 70 degrees, not 170, 70 degrees. And L effective equals to L1 for single lacing and 0.7 times L1 for double lacing. Double lacing means if you are providing like this also. If this is single lacing and this one would be double lacing. This is double lacing. Fine. So single lacing and double lacing, that is what we'll be seeing over here. So theta should be in the range of 40 to 70 degrees as per the code, and L effective equals to L1 for single lacing and 0.7 times L1 for double lacing and 0.7 times L1 for welded lacing. Width, generally for lacing you will be providing only one dia hole. So here if you see, you will be providing only one bolt over here. Fine. So width would be 3 times of the dia of the bolt. If dia of the bolt is 20 mm, width would be 60 mm. If it is 22 mm, it would be 66, approximately 65 mm. So width of the lacings is generally 3 times nominal dia of the bolt. Thickness of the lacing is generally given as L1 upon 40. L1 is the effective length upon 40 for single lacing and L1 upon 60 for double lacing. Fine. Next, to prevent buckling of the component, see, To prevent buckling of the component, lambda of component should not be more than 50 or 0.7 times lambda of the column, right? So what exactly this means? Prevent the buckling of the component means, in order to prevent this component, in order to prevent buckling of this, C upon R minimum, this is lambda of component. Fine. Lambda of lacing, if they say what is lambda of lacing, it should not be more than 145. Okay, so that is L1 upon R minimum. That should not be more than 145. From here you have to calculate L1, or from spacing also you can calculate L1. If you know the spacing between the columns, you can calculate L1, and from here you can calculate spacing between the lacings. Okay, this is one of the point, and that should not be more than 50 or 0.7 times lambda of column, right? Minimum of these two things. Lambda of component should not be more than 50, or it should not be more than 0.7 times lambda of the column. Fine. And throughout the length of the column, lacing should be of same thickness and width. On opposite sides, lacing system provided on the opposite sides of main column should be mirror image to each other. If this is the column, lacings provided on the opposite side of the main column should be mirror image of each other. Should be mirror image of each other. Fine, should be mirror image of each other. Next, arrangement of the lacings. Which one is better, this one or this one? Generally this one is better. Why? Because here if a bolt fails, then spacing will be doubled. Automatically there will be buckling over here. Even if a bolt fails here, there is another bolt here, so spacing will not be doubled, there will not be buckling. So this type of arrangement is preferred over that type of arrangement. This is arrangement of lacings. Next, forces acting in the lacing. Forces acting is generally transverse shear. So that is equals to 2.5% of column loads. Lacing systems are designed to take 2.5% of the column loads. If load applied on the column is P, then load transferred on the lacing shear is transverse shear is 2.5% of the column load, and that is shared equally by both the lacings. In the main column, on the opposite sides, lacings are provided, so the load applied to shear, load taken by lacings is 2.5% of total load, and that is taken by both the things equally. Fine, that is taken by both the lacings equally, lacing system equally. That is transverse shear. So whatever we are designing, we will be designing for that transverse shear only. Okay. Fine, these are the major points from exam point of view. So whenever you are going to design, first design a built up column, provide the spacing, next design the lacing member. That's it. Fine, you can design the lacing member accordingly. Angle designing means finding out the length, width, thickness and force acting on it. That's it. Designing of battening members. Battening members are horizontal members and they are subjected to moment. Battening members are horizontal members and they are subjected to bending moment. Unlike lacing member, battening members are subjected to bending moment. Fine. If let us say spacing between the center to center spacing is S, or end to end spacing is S1. So this is the S1, that is the spacing, and if you want to find out the length, S1 plus this clear ends, you'll just add, that would be the length of the battening. Anyway, lacings are designed as axial members. Battening members, battens are designed as frames. Frames means it takes bending moment also, whereas a lacings takes only horizontal force. Lacings takes either axial tension or compression. Fine. Okay, these are the things. Next, these are called as end battens and these two are called as intermediate battens. The designs will be different for it. If battens are used, then effective length is increased by 10%. If effective length is increased by 10%, lambda value will be increased. If lambda value is increased, then automatically permissible compressive stress will be decreased. That is the idea. So why, sir? In order to take care of the shear deformations of the column. Because of providing battenings, there will be some shear deformations. In order to avoid that, we are going to increase the effective length by 10%. If you increase effective length by 10%, automatically everything will change. Lambda value will change, sigma AC will change. If sigma AC is changed, then load carrying capacity will be decreased. If battens are used, load carrying capacity decreases. Fine. Next, say everything. Lambda of component should not be more than 50, or it should not be more than 0.7 times lambda of column. From this, you will get the spacing between the battenings. Fine, that is one thing. And effective depth of the intermediate batten should not be less than 3 by 4 times alpha, or it should not be less than 2 times B. It should not be less than 3 by 4 times alpha, or it should not be less than 2 times B. Fine. So B is width of column component, and alpha equals to centroidal distance between column components. If X is the clear spacing, X plus 2G. If this is the centroid, sorry, X plus 2 times CYY. So X plus 2 times CYY, that would be your alpha. So intermediate battens, if I am talking about intermediate battens, depth of the intermediate battens, it should not be less than 3/4 alpha, and it should not be less than 2 times B. And effective depth of N batten, it should not be less than alpha, and it should not be less than 2 times B. And minimum thickness of the batten, it should not be less than S1 upon 50. So overall depth would be equals to N batten plus D end plus 2 times edge distances. If welding is done, D end equals to D end. Overall depth of the end batten equals to depth of the end batten plus 2 times edge distance. Minimum thickness of batten, it should not be less than S1 upon 50. What is S1? S1 is clear spacing, or distance between the innermost connecting lines. That is X plus 2G. X is the clear spacing, G is the gauge distance. That means from the bolt to the end of the channel. CYY is the centroidal distance. Alpha is B X plus 2 CYY. S1 would be equals to X plus 2G. Fine. C equals to something like that. So minimum thickness of batten S1 upon 50, there it is L1 upon 40, L1 upon 60, it is S1 upon 50. And effective depth of end batten should not be less than alpha, it should not be less than 2B. And effective depth of intermediate batten 3/4 of alpha, and it should not be less than 2B. Fine, these are the things. Apart from this, forces in the battens are also designed for 2.5% of the column load. So V equals to 2.5% of the column load. Transverse shear force is shared by parallel planes of battens equally. So number of parallel planes here 1, 2. Fine. So transverse shear force equals to V upon N, that is V upon 2N. Now whenever you are going to design for it, you have to just draw free body diagram. So here it is V is the column load. Fine. Sorry, V is the force on the battens, that is 2.5% of column load. N is the number of parallel planes, that is equally by these two things. So V upon 2N here, V upon 2N here. Total action is V upon N, reaction is V upon 2N, V upon 2N. Fine. So based on these reactions, you will be designing for a force of VC upon NS. Where C is the spacing between the battens. S is the distance between the centroidal groups or bolts indirectly. X plus 2G over there. So, and it will be designed for a moment of VC upon 2N. So battens are designed for a moment of VC upon 2N and a force of VC upon NS. Fine. So these are the points. Battens are the members subjected to the bending moments, whereas lacings are designed as the truss members, that is for axial forces and for tensile forces and compressive forces. See, I am giving basic idea about it because up to here in the gate you can see they'll ask what is the load taken by lacing, and what is the lambda for the lacing, and what is the lambda of the component of lacing member, 50 or 0.7 times lambda for lacing member is 145, and load taken, transverse shear taken by the lacing or batting is 2.5% of the column load. So that is why you have to remember these points and apply it. Not designs are not expected in the gate, so that's why I am not designing anything over here. Fine, just giving a basic idea regarding each and every thing. You should know the difference. Battenings are horizontal members, lacings are inclined members, and accordingly we are going to design it. Depth, width, all those things, these points you have to remember. That is the important thing that you have to remember. Okay, next, design of column splices. Fine. So splices are the one which is provided in order to increase the strength of the column. If you see, this is the web splice, or which is also called as web cleat. This is called as flange splice. Generally, web splice is provided at a distance of h by 3 to h by 4 from floor level. Here also it is provided at a distance of h by 3 to h by 4 from the floor level. These are positions where splices are provided. This is web splice. This is called as flange splice because these are flanges. This is web. This is called as web splice, and that is called as flange splice. Fine. So this is the idea. Splicing is provided in order to increase the length of the column. Find the most suitable location for column splicing is at a distance of h by 3 to h by 4 from top or bottom. That is what it is being said over there. So here generally while splicing, if you see, column is transfers load by bearing action. Here if splicing is not done, what exactly happens? From here to here, the load is transferred by bearing action because both the things are in contact with each other. Whereas here splices are provided at the ends. A gap is provided. When load is applied, this will be taken by this splice and it will be transferred over here, and finally it will be transferred onto the column. That is the idea. So splicing is provided in order to increase the length. As the same thing here, you can easily transfer the load. A gap of 0.01 mm may be assumed over there. Fine. So this is the idea. Generally, column splice, if column ends are not machined for complete bearing, then entire load is assumed by the bearing action only. Those splices, plates and its connections. In this case, splice plates and connections are designed for a force of P by 2 plus M upon H. Here, if you see, if a column is subjected to moment M, then also splice plate must also resist additional force of M upon H. Like, if a moment is provided, and this is H. If let us say the distance is H, M upon H, P by 4 plus M upon H. If column ends are not machined, if it is machined, then it is P by 4 upon M upon H. It can easily take by bearing action. If they are not machined properly, then an additional load, then a heavy load has to be taken by the flange splice, that is P upon 2 plus M upon H. Fine. And strength of the plate is width multiplied with thickness multiplied with permissible axial stress, that is 0.6 times Fy. If columns ends are machined, then the load taken by P by 4 plus M by H should be less than or equal to Bt sigma AC. If loads are not machined, P by 2 plus M by H should be less than or equal to Bt sigma AC. Fine. This is how you are going to find out the things. And web splice. If V is the shear force acting on the web splice, calculated shear stress in the web splice equals to V upon 2 multiplied with L1 multiplied with T. This is the web splice. Anyway, the calculated shear stress should be less than or equal to permissible shear stress, that is 0.4 times Fy. So idea is very simple. Whenever a splice is provided, the load is instead of bearing action, load is transferred by the splice plates. So that would be equals to P by 4 plus M by H or P by 2 plus M by H. Calculated shear stress equals to V upon 2 multiplied with L1 multiplied with T, that is equals to 0.4 times Fy. Fine. So if column ends are machined or not, you should know that if column ends are machined properly, then it is P by 4 plus M by H. If it is not machined, then it is P by 2 plus M upon H. Fine. So whereas H equals to the distance between these two things. Fine. So this is one of the point that you have to remember. Column splice and web splice. Next one is design of column bases. Design of column bases, idea is very simple. This is a base plate. From column to the foundation it should be transferred, and this is the base plate, and you are going to provide a cleat angles, something like this. That is column, this is base plate, and this is cleat angles. So if you see over here, this is the column, fine. So below this is here there are cleat angles, fine. This is base plate. Load has to be transferred from column to the foundation. These are ankle bolts, and these are cleat angles, small pieces of angles. So whenever we are going to design for it, these are different types of foundations. Anyway, the idea is majorly how to find out the thickness of column base, that equals to 3W upon sigma bs a square minus b square upon 4 in WSM, and 2.5W upon sigma bs a square minus 0.3 b square in LS. So this is one of the thing where W is the upward pressure on base plate, A and B greater and smaller projection of base plate beyond column edge respectively, permissible bending compressive stress in base plate, fine. So these are the points that you have to generally remember in design of base plates, fine. Next chapter is in this revision session is design of compression members. Revision has to be, in order to make it crisp and quick, I am using the PDF notes that I am having and trying to explain it from this notes, fine. So it's just like mind revision, whatever that is we have read. Okay, these are the concepts that is there, these are the formulas, and this is how you have to apply the formula, and this is the major thing, fine. That is how it goes. So design of compression members. In design of compression members, the first thing that compression members means columns. Columns are generally compression members that are used in the buildings. Struts are the compression members that is used in the trusses, fine. So these are the major compression members. Here whenever I am designing it, I mean that we are going to find out load carrying capacity of it, and we are going to find out the cross sectional area of it. The major problem, whenever the column comes into your mind, the major problem you have to think about is the Euler's load, that is effective length, slenderness ratio, and what are the values of the slenderness ratio. Slenderness ratio starts from 180 and it ends at 400, fine. So that is the idea that you have to remember. So maximum slenderness ratio for compression members is 180. Maximum slenderness ratio for tension members is 400. Maximum slenderness ratio for the members subjected to the reversal of stresses, tension members subjected to reversal of stresses is 350. Reversal of stresses means for normal live loads and dead loads it is tension, and for wind loads if it is compression. Compression is always a major problem. There is a problem of buckling in the compression members, fine. And effective length of the columns. Effective length of the columns, if one end is fixed means restrained against rotation. It can't rotate, it can't translate. So restrained against rotation and translation, fine. One end is fixed, other end is free. So critical load if you have to calculate, that is pi square EI upon L square. Effective length L equals to 2L, fine. So that is 4L square. If both ends are pinned, effective length equals to L equals to L. So critical load equals to pi square EI upon L square. And if one end is fixed, other end is hinged. Fixed means restrained against rotation and translation, and other end is hinged, then effective length equals to L upon root 2, fine. L effective equals to L upon root 2. And radius of gyration, always remember, radius of gyration, it is generally like, if total area is concentrated at a distance of some xx, kxx or r from centroidal axis, that distance is called as radius of gyration. It is generally given as radius of gyration is generally given as ixx upon a. If it is kxx, it is ixx upon a. That means indirectly, if it is radius of gyration in xx direction, it is ixx upon a. If it is in yy direction, then it is ryy equals to under root of iyy upon a. Under root of iyy upon a. Fine, these are the two cases. The load carrying capacity of the column with one end fixed, other end free is P. If free end is made fixed, then load carrying capacity will be increased. Fine. So pi square EI upon L square. You have to remember this. You don't have a choice. Generally, critical load is pi square EI upon L square, L effective whole square. L, if both ends are fixed, it is 2 times or L by 2. If it is one end is fixed, other end is free, then it is 2L. Fine. So effective length is what that makes an important thing over here. As I said, Euler's critical load, that is generally given as pi square E I minimum upon L effective square. Pi square E I minimum upon L effective square, and this can be written as pi square E A multiplied with R minimum square upon L effective square. So that would be equal to pi square EA upon L effective upon R minimum whole square. L effective upon R minimum is called as slenderness ratio. So this PCR would be equals to pi square EA upon lambda square, where lambda equals to L effective upon R minimum. L effective upon R minimum. Pi square lambda slenderness ratio equals to L effective upon R minimum. Fine, this is one of the thing. So always remember, you have to take R minimum. So if you know R minimum, you can find out I minimum. L effective upon R minimum would be equals to I minimum upon A, under root of I minimum upon A. So load carrying capacity for long column depends upon flexural rigidity and axial rigidity. Slenderness ratio lambda equals to L upon R. Fine. So one end is fixed, other end it is restrained against rotation, but it is free to translate. Other end is restrained against rotation and it is free to translate. L would be equals to 1.2 times small l, and L equals to if one end is hinged, other end is restrained against rotation but it can free to translate, then L effective would be equals to 2 times L. One end is hinged, other end is free to move, then L effective will also, like it can move and it is restrained against rotation. Fine. So that is one of the things. So these are the different criterias. Accordingly you have to find out what is the L effective. Fine. Once you find out the L effective, use L effective and get the answers. Okay. Now once if you know L effective, generally sigma AC, permissible compressive stress. If you want to find out load carrying capacity, logic is very simple. Load carrying capacity in anything, design of compression members also, in design of compression members, load carrying capacity equals to sigma AC multiplied with area. Sigma AC multiplied with area of compression member. Fine. So sigma AC, generally you will get this from the lambda value. It actually depends upon lambda value. PCR equals to pi square E I minimum upon L effective square. Fine. Pi square E I minimum upon L effective square. So pi square EA R minimum square upon L effective square. So that is equals to pi square EA upon lambda square. Pi square EA upon lambda square. This is P critical, right? So based on the value of lambda, you will get sigma AC. Generally based on a table will be given to you. Yeah, there are different formulas, but generally I'm saying if you want to find out sigma AC for lambda values, different lambda values, sigma AC will be given to you. See, P critical upon area, that would be equal to sigma critical, that is equals to pi square E upon lambda square. Sigma is inversely proportional to lambda. If lambda is more, sigma would be less. Fine. So our major idea is to find out the lambda value, L effective upon R minimum. Based on that, you'll get all your answers. Fine. So sigma AC is generally 0.6 times Fy, or it is 0.6 times FCC, Fy upon FCC to the power of n plus Fy to the power of n whole to the power of 1 by n, where n is the imperfection factor. Fine. This is one of the thing. Next, These are stable equilibrium, unstable equilibrium, and all those things. Not a bigger issue. If you if you release the ball anywhere, if it comes back to its original position, then it is stable equilibrium. If you just push the ball, it goes and stops somewhere else, then it is neutral equilibrium. If you just touch it, if it disappears, if it is unstable, that is unstable equilibrium. Fine. Unstable equilibrium. Effective length of the struts. Effective length of the struts. So effective length of the struts, this is continuous strut, this is discontinuous strut. If strut is between the two joints only, then it is discontinuous strut. If strut spans over many joints, then it is continuous struts. Fine. Then it is continuous strut. Effective length. For discontinuous strut, effective length is L and axial compressive stress is 0.8 times sigma AC. Fine. So that means here, if a strut is connected by the single bolt, if a strut is connected by the single bolt, effective length is L and permissible stress is reduced by 20%, 0.8 times sigma AC. If a single angle discontinuous strut is connected by more rivets, if there are 2 rivets over here and if there is a well over here, then effective length is 0.85 times L and permissible axial compressive stress is sigma AC. Fine. This is one thing, sigma AC. Now, local buckling of flange and web plates. This is one of the important discussion that we have to keep. Local buckling of the flange, or buckling of the compression flange. All those things, if you have to see, if let us say this is an I section, this is compression flange, this is web, this is tension flange. If I take this is B is the width. Fine. So it tries to buckle like this. In order to avoid this, the value of B should be reduced, or value of B by T should be reduced. Fine. For if you have to find out critical stress, in that case it is given as K pi square E upon 2L into 1 minus mu square multiplied with B by T whole square, B upon T whole square. Fine. So this is one of the thing. So in order to prevent local buckling of the flange, B upon TF should not be more than 16. At the same time, depth of the web and thickness of the web should not be more than 50, and B upon TF should not be more than 8.4. Recently in LSM, in the new code, you will be seeing BF upon TF. Width of the flange upon thickness of the flange should not be more than 8.4 and depth of the web upon thickness of the web should not be more than 50. Fine. And BF upon TF should not be more than 16. See, if it is connected by the bolts, this is the B that you are going to take, and if it is played something like this, here this is the B. B would be from the outside of the web, width of the flange if I am talking about. Here width will be taken from away from the bolt, last bolt, that is B. That should not be more than 16 or 8.4. dW by TW should not be more than 50. If that condition is satisfied, then there will not be local buckling of the flange. If there is no local buckling of the flange, then it is very simple. Just find out the lambda value. Idea is find out the lambda value corresponding sigma AC. You will know. If you know sigma AC multiplied with area of compression member, you will get your answer. Fine. Okay. So this is one of the thing. So this is how you will design a compression member. Next, analysis of struts. Struts are like compression members in the trusses. Fine. If I take this as a strut, this is a strut connected to a gusset plate. So by the structural bolts, these are tack rivets. Fine. L1 is the pitch of the tack rivets, that should not be more than 600 mm. If it is tension member, it should not be more than 1000 mm. We have already discussed that. Fine. So if I take this is the gusset plate, onto the opposite sides of the gusset plate, if members are connected something like this, on the opposite side of gusset plate, if two angles are connected like this, between struck the track rivets to prevent buckling of the component. So what happens is, now there is a possibility of buckling of this component. Between the tack rivets, strut can buckle. In order to avoid that, lambda of the component should not be more than 40 and it should not be more than 0.6 times lambda of the strut. Fine, lambda of the strut means lambda of the column, that equals to L effective upon R minimum of whole column. If you are talking about that component 40 upon 0.6 times lambda of the strut. So that is equals to, if I have to calculate lambda of this component, effective length would be L1. L1 upon R minimum. R minimum for that small angle, that would be RUU or RVV. And if I have to calculate lambda of the strut, that is L upon R minimum of built up strut or column. Okay, L effective upon R minimum of built up strut or column. If this is RXX, RYY, this is total strut, built up column or strut. Fine. So generally we'll make RYY is minimum since it is made built up. So we will take that RXS. We design in such a way that RXX is minimum. Fine. So that it will be strong and there will not be any lateral buckling. So we'll be taking R minimum equals to RXX, lambda of the strut equals to L upon RXX. Fine. And lambda of the component L1 upon R minimum. For a single angle it is RUU and RVV. So once that is solved, the idea is you have to make sure that a component is not going to buckle. Component of strut is not going to buckle. Component of strut is not going to buckle. And component of strut is not whole strut. That is whole strut, that is a compression member. Whole strut, that is a compression member, that is L effective upon R minimum of built up strut or column. Fine. So R minimum for a built up strut or column equals to RXS RYY. For a single column it is RUU and RVV. Fine. So these are the points that you have to remember. You can calculate load carrying capacity by calculating R minimum of built up strut or column. Once you calculate R minimum, find out lambda. Once you know lambda, a table will be given to you between lambda and sigma AC. Sigma AC multiplied with total area will give you the load carrying capacity, and we have to cross check with the cross check so that component is not going to buckle. So in order to prevent the buckling of the component, you have to cross check this. If it is okay, this is done. Fine. So this is how we generally design a compression member or struts. Fine. Our next concept is design of tension members. Till now we have seen design of connections, bolted connections, welded connections. We have done something in the plastic analysis. Now we will be seeing design of tension members. Fine. So tension members means members that is subjected to the pull. Fine. Members that is subjected to the pull. The major problem in the tension members is shear lag. Shear lag is non-uniform straining of the member. That means if you apply the load something at the ends, total A will not be strained uniformly. Generally you will see there is a non-uniform straining. That means the area near to the load will strain more compared to that of area far away from the load. So this is the shear lag effect. If they ask what is shear lag effect, that is the shear lag effect. Fine. Next one is if there is long joints. If there is long joints, if length of the joint is more than 15 times dia or 150 times throat thickness in the welded connections, then it is called long joint. Fine. So if this is the long joint, the major thing is when you apply the load, generally we assume that all the bolts will take equal amount of the load, but in actual it is different. So what happens is whenever you apply the load, so N bolts will take more load compared to that of the near bolts. So what happens is if at all failure occurs, there will be unbuttoning effect. It is like totally unbuttoning effect. That means it totally first failure, like just if you remove your button, what are the effect you will see? The same unbuttoning effect you will be seeing over here. Next one is grip length. So if you remember, I have already discussed what exactly is grip length, and grip length should not be more than 5 times dia of the bolt. Why? In order to avoid the bending stresses. So here, because of the loads, there will be shear here and there will be some bending stresses. There will be some bending because equal and opposite forces are separated by some distance. There will be couple. Because of that, there will be bending. So bending stresses will be developed inside it. Fine. So there will be bending stresses, and grip length, if it is, should not be more than generally 5 times dia of the bolt. That is one thing. Fine. Next, so in order to avoid shear lag effect, what is shear lag effect? Non-uniform straining. In order to avoid shear lag effect, we are going to use small piece of angle that is called as lug angle. That is called as lug angle. Fine. So this is one thing. Lug angle is a small piece of angle. That is one more thing. Next, next point is load carrying capacity of the tension member. Generally, if they ask what exactly is load carrying capacity of the tension member, that is permissible stresses or allowable stresses in the tension member multiplied with net area. Fine. Safe load carrying capacity in WSM and safe load carrying capacity in LSM. If they are safe load carrying in the WSM, always remember, if they ask what exactly is safe load carrying capacity, safe load carrying capacity, safe load carrying capacity A net multiplied with sigma AT. This is in WSM, and the same value equals to A net multiplied with 0.9 FU upon 1.25 or gross area multiplied with Fy upon 1.1. This is in LSM. Fine. Safe load carrying capacity of the tension member. Whatever, even if it is compression member, if they are asking, the idea is simple. Stress multiplied with area. And same thing, we have seen that in the bolts. Fine. So here also, if they ask A net equals to same B my, suppose if you are taking any member, if it is B, then A net would be equals to B minus, let me check whether mic is on or not. Mic is on. Fine. So A net would be equals to B minus 3D multiplied with T. This is A net. Fine. So whereas gross area, if they ask, gross area would be equals to B multiplied with T. This is gross area and that is net area. In LSM and in WSM we have seen. Fine. Calculation of A net. Different types of riveting you will see. The one of the most important concept over here is staggered riveting. That is what you have to remember. In staggered riveting, you have to check something like this. If it is for every cross leg, you have to add S square upon 4G. Fine. S square upon 4G, or between these two bolts. That means if the failure is something like this, if the failure is something like this, what exactly you will be doing? A net would be equals to B minus 3D plus, because of one inclined leg, this is equals to R1 square upon 4G. The distance between these two, pitch between these two is S or R1. This is R1, this is R2, plus this also R2 square upon 4G2. whole multiplied with t, whole multiplied with t. Fine. So this is how we generally try to find out A-net for staggered riveting. For every inclined leg, we are going to add an amount of S square upon 4G. So R1 square upon 4G, and here also R2 square upon 4G2. You have to check different criteria here. Failure along this, failure at this like this, or failure only along this location. Fine. So different types of failure you will check, and minimum of all those values you will be taking as the A-net. And A-net multiplied with sigma AT will be giving you the load carrying capacity. Fine. So this is one of the problem. One of the concept. I am discussing only concepts here. Why, sir? Why you are discussing only concepts? Because this is revision. This is not problems. For problems, you just solve your problems on your own. Previous year's gate questions is enough at this point of time. Next one is, if single angle tension member is connected to the gusset plate. This is a single angle tension member that is connected to the gusset plate. Fine. So this is tension member that is connected to the gusset plate. A-net would be equals to A1 plus K times A2. A1 plus K times A2, where K equals to, generally given as 3A1 upon 3A1 plus A2, where A1 is the net area of connected leg and A2 is the gross area of outstanding leg. This is called as outstanding leg. This is called as outstanding leg, and this is called as connected leg. This is connected leg, this is outstanding leg. So A1 is the net area of connected leg. Net area means you will remove the holes. That is net area of connected leg. Net area of connected leg. A2 is gross area of outstanding leg. Gross area of outstanding leg. That equals to this width multiplied with t. Simply b multiplied with t. So you will be using a factor of k. Sir, why we are using a factor of k? We are using a factor of k because in order to overcome the shear lag effect. Because load is being applied over here, there will be non-uniform straining. In order to avoid that, we will be using a k value. If a single angle is connected to the gusset plate, k equals to 3A1 upon 3A1 plus A2. Fine. Now, if two angles back to back are connected to the same side of gusset plate, here two angles are there that is connected back to back on same side of gusset plate, not opposite side, on same side of gusset plate. Fine. So here in order to overcome the shear lag effect, k value here would be 5A1 upon 5A1 plus A2. Shear lag effect will be less here. We will not say it is totally removed, it is less. So A-net would be equals to A1 plus K times A2, where K equals to 5A1 upon 5A1 plus A2. This is one of the important thing, 5A1 plus A2, that is A-net. And A-net in the previous case is 3A1 upon 3A1 plus A2, and A-net in this case is 5A1 upon 5A1 plus A2. Fine. This is one of the important thing. Next, if there is no shear lag effect, or next one is, if two angles are connected on back to back of the same opposite side of the gusset plate, on this side and behind this. This is one of the most efficient connection, because there will not be any shear lag effect in this. So since there is no shear lag effect, then A-net would be equals to A1 plus A2, K equals to 1. There is no effect of shear lag in this. A-net would be equals to A1 plus A2. Simply you can calculate. So A2 here would be net area of connected leg, not gross net area. That means gross area of angles minus area of rivet holes. Gross area of angles minus area of rivet holes will give you the net area. So simply you can calculate from here. So idea is very simple. If single angle is connected to the gusset plate, A-net equals to A1 plus K times A2, where K equals to 3A1 upon 3A1 plus A2. And if two angles are connected on same side of gusset plate, K equals to 5A1 upon 5A1 plus A2, and total A-net is A1 plus A2. And finally, if two angles are connected on opposite side of the gusset plate, A net would be equals to A1 plus K times A2, where K equals to 1 over there. Fine. So that means there is no effect of shear lag in that case. And finally, there are problems. Idea is to calculate A net. Minimum value of A net is what? You'll try to see all the failure cases. That means suppose if they are asking in this question, what exactly is the failure? What exactly is the A net? There is a problem, load is being applied. What exactly is A net they are asking? What exactly is A net they are asking? Failure can be along this, it can be along this, or it can be along this, something like this. That means if I have to show failure can be along 1 1, failure can be along 2 2, failure can be along something like this 1 3 2, or failure can be along 1 3 4 1. It can be like this also, failure. You have to check all the failure cases. If along 1 1, if they ask A net, what you will do? A net would be equals to B minus 2D into T. B minus 2 times dia of the holes. If they ask along 2 2, along 2 2 A net, along 2 2 A net, that is equals to B minus D multiplied with T. Along 1 3 4, along 1 3 2, if they ask along 1 3 2, along 1 3 2, A net equals to B minus 2D plus S square upon 4G multiplied with T. That is A net. Fine. And if they ask along 1 3 4 1, along 1 3 4 1, A net equals to B minus 3D plus 2 inclined legs, S square upon 4G, S square upon 4G, plus S square upon 4G, plus S square upon 4G, whole multiplied with T. This is A net. So along 1 1, along 2 2, along 1 3 2, along 1 3 4 1. These are the 4 things. Minimum of all these values will be taken as A net. Minimum of all these things will be taken as A net. Fine. So this is one of the problem. And A net multiplied with sigma AT will give you the answer. This is what majorly we'll see in the tension members. Design of lug angle is generally we don't see that in the gate, so I'm not discussing it. But lug angle is used to reduce the shear lag effect. That is one thing that you have to remember. I think this is what maximum you will see in the tension members. Fine. So we are doing the steel quick revision. I'm going at a very fast rate, I know that, and I'm using the notes to explain the thing. I'm not writing everything, so I hope you'll understand what is what. Fine. Next one is welded joints in the connections only. Still till now we have seen bolted connections or riveted connections. Now we will be seeing welded connections. So in welded connections, you have to remember that maximum we will be using the fillet welds. Fillet welds is something like this, which is done at the corners. Fine. And this is the size of the weld. This is called S, size of the weld, and minimum thickness is the throat thickness, right? This is the throat thickness and this is the size of the weld. So T is the thickness and S is the size of the weld. So idea is very simple. If they ask what is the strength of the weld, area of the weld multiplied with shear strength, because welds are subjected to only shear. It is not subjected to tension. Whatever the force that you apply, the welds, the force is transferred to the other plates in the form of shear only. So here, whatever the load that you are applying over here, this is transferred in the form of shear. So it can be horizontal shear or vertical shear. If let us say this is the size of the weld, S is the size of the weld, T is the throat thickness. S is the size of the weld and T is the throat thickness, and these are fusion phases. Fusion phases. Then throat thickness is called minimum size of the weld. Fine. Now in that cases, fine. So what should be the as I said, load will be transferred in the form of shear. Here if you say this is the eccentric connections, because of this there is some bending moment and shear force. Because of load there will be vertical shear force, and because of bending moment there will be some horizontal shear force. So load will be transferred in the form of shear. Load will be transferred in the form of shear, vertical shear and horizontal shear. And angle between the fusion phases, it should not be less than 60 degrees and and it should not be more than 120 degrees. Why, sir? If it is less than 60 degrees, you can see here the these are fusion phases. The angle should, if it is less than 60 degrees, then it is difficult to do welding. Generally we do that arc welding. You might have done in your first year engineering. You'll do that arc welding and all those things. So here the welding should be done, and you can't do the welding if it is more than 120 degrees. If it is more than 120 degrees, then what happens is the size thickness would be very less. So the angle between fusion phases generally should be in the range of 60 to 120 degrees. So, and throat thickness is generally given as K times S. This is the throat thickness. Throat thickness is the minimum thickness of the weld. S is the size of the weld, T is the throat thickness, right? S is the size of the weld, T is the throat thickness. S equals to size of the weld, T equals to throat thickness. Throat thickness is the minimum thickness. Throat thickness, minimum thickness. Throat thickness, that is minimum thickness. T equals to K times S. Fine. Whereas K depends on the angle between the fusion phases. Angle between the fusion phases. If angle between the fusion phases 60 to 90 degrees, K value is 0.7, and if it is 91 to 100 degrees, K value is 0.65, and if it is 101 to 106 degrees, 0.6, and 107 to 115, 0.55, and 114 to 120, 0.5. So K value will be from 0.7 to 0.5. 0.7, 0.65, 0.6, 0.55 and 0.5. This is 0.60. Fine. You have to remember, if you want to prove, you can prove, but it's better. From 60 to 120 degrees, the value will be from 0.7 to 0.5. So generally you will take 0.5 only. So generally we'll take 0.7 only. If nothing is mentioned, assume the angle between the fusion phases is 90 degrees and it would be K value is 0.7. Throat thickness is 0.7 times S. So now if it is throat thickness is 0.7 times S. Next one, minimum size of the weld. Size of the weld, minimum size of the weld depends upon thickness of thicker plate, not thinner plate. Fine. Thickness of thicker plate. Minimum size of the weld depends upon thickness of thicker plate, so that there will not be any residual stresses. In order to avoid the residual stresses, so minimum size of weld depends upon thickness of thicker plate. So if thickness of thicker plate is up to 10 mm, minimum size is 3 mm, and if it is 11 to 20, minimum size is 5, and if it is 21 to 36, and if it is more than 30, it is 32, it is 8 mm. Minimum size of the weld. You should not provide less than this. It actually depends on thickness of thicker plate. If two plates are welded, it depends upon thickness of thicker plate. Fine. And maximum size of the weld depends upon thickness of thinner plate, so that uniform welding can be provided. So maximum size of the weld, it depends upon thickness of thinner plate, and it is generally thickness of thinner plate minus 1.5 mm if it is square plates. If it is rounded plates, it is 3 by 4 times T, where T is the thickness of thinner plate. Fine. Just a minute, let me check whether mic is on or not. Mic is on. So T is the thickness of the thinner plate. Fine. So always remember, if maximum size of the weld depends upon thickness of thinner plate, minimum size of the weld depends upon thickness of thicker plate, and up to 10 to 32 mm, the variation would be 3 to 8, and here it would be thickness of thinner plate minus 1.5 mm if it is square edges, or it is 3/4 time T if it is rounded edges. Now once if you find out the thickness, next you should know the effective length of the weld. Effective length of the weld would be actual length of the weld minus 2 times the size of the weld. You can remove this. Here let us say, if this is the front view, there is a T section and these two things are welded at the sides, and if you are seeing from the side, it will be looking something like this. So effective length would be equals to actual length minus 2 times size of the weld. Actual length minus 2 times size of the weld. So if it is effective length is actual length minus 2 times size of the weld. So finally, if they ask what is the effective cross sectional area of the weld, effective cross sectional area of the weld, effective cross sectional area, or area effective in resisting shear strength, effective cross sectional area of weld, that would be equals to throat area, that is throat thickness multiplied with effective length, throat thickness multiplied with effective length. When throat thickness is K into S multiplied with effective length is L effective. K into S and effective length is L effective. When this is one of the thing, and load carrying capacity of the weld is permissible shear stress in the weld multiplied with effective area of the weld. So what is the permissible shear stress in the weld? Fs equals to 110 MPa, and that equals to Fu upon root 3 multiplied with 1.25. Fs equals to 110 MPa, and that is equals to Fu upon root 3 multiplied with 1.25, that is LSM. Ultimate tensile stress in weld metal, this is 110 MPa, and this is Fu upon root 3 multiplied with 1.25, ultimate tensile stress in weld material. So always if they ask what is the strength of the weld, permissible stress in the weld multiplied with effective cross sectional area. Strength of the weld permissible shear stress of the weld, multiplied with effective cross sectional area, multiplied with effective cross sectional area. Permissible shear stress in the weld, if I have to ask, Fs multiplied with cross sectional area Ks multiplied with T. Fine. Where S is the size of the well, T is the throat thickness, and Fs is the permissible shear stress in the well, and that value equals to 110 MPa, and this is equals to Fu upon root 3 multiplied with 1.25. This is as per LSM and this is as per WSM. Fine. Now that is the thing. Next, so intermittent wells, pitch of the wells. If they ask, generally instead of providing the whole length, we'll be providing intermittent wells. Pitch of the wells, if they ask, same thing. If it is compression members, pitch of the wells should not be more than, if our member is subjected to compression, pitch of the well should not be more than 12T or 200 mm, and if it is subjected to tension, pitch of the wells same as that of bolts, that is equals to 16T or 200 mm, where T is the thickness of the thinner plate. This is pitch of the wells. For wells in compression, maximum pitch is equals to 12, minimum of 12T or 200 mm. For wells in tension, maximum pitch equals to minimum of 16T or 200 mm. Next one is slot welding. If the length is not, if you are welding, if length is not sufficient, then you will be welding at the slots. You will be welding at the slots. So width of the slot should not be less than 3T and it should not be less than 25 mm. Maximum of 3T and 25 mm, where T is the thickness of the thinner plate. Fine. So these are the certain points that you have to remember in the welds. And next one is longitudinal and transverse shear. When load is applied like this, when you are applying the load, let us say if there is a load P over here, if you are applying the load like this load is resisted by this shear and this load is resisted by this shear. This is called as longitudinal shear, and shear because of this is called as transverse shear. Fine. This is called as longitudinal shear in the fillet weld, and this is called as transverse shear in the fillet weld. Fine. So P1 would be equals to this length multiplied with throat thickness multiplied with Fs. P2 would be equals to this length multiplied with throat thickness multiplied with Fs. P equals to this length multiplied with throat thickness multiplied with Fs. Fine. So total P is taken by P, P1 and P2. These are the points. So always remember, whenever we talk about the welds, in the welds, the size of the weld is first of the important thing. Throat thickness, and throat thickness depends upon the angle between the fusion faces, 60 to 120 degrees. So it varies from 0.7 to 0.5 throat thickness, and effective length of the weld. So effective length multiplied with throat thickness will give you effective area, multiplied with permissible shear stress in the weld will give you the strength of the weld, and permissible shear stress in the weld is 110 MPa, or it is Fu upon root 3 multiplied with 1.25. Fine. As per LSM, WSM, LSM we have seen, and maximum pitch of the welds for members in compression, or if member is subjected to compression, and maximum pitch of the welds if member is subjected to tension, 12T or 200 mm, 16T or 200 mm, where T is the thickness of the thinner plate. Fine. So these are the points that you should generally remember. Fine. And longitudinal welds, we also have seen the slot welding and all the other things, and we have to always make sure that there is no stresses in the welds. There is no stresses in the welds. We'll see this type of problem also. Like if load is being applied over here, load is generally applied at the centroid. Then you have to design that in such a way that there is no additional bending stresses. That means if this is P1, P2, P3, fine, P1, P2, P3, the load is being applied at the centroid, then you have to design that in such a way. So first one is P equals to P1 plus P2 plus P3, and next one is moment about centroid should be equals to 0. Fine. Moment about centroid equals to 0. So that means P1 into this distance, P3 into this distance, P2 into this distance. If you do that only, you can easily solve the things. Or if I have to show in a better way, I'll show it here. Yeah. So let us just see here. Here there is a gusset plate and there is an angle section. Both are connected by the wells. Both are connected by the wells. Fine. So here these two things are connected by the well, and load is generally applied at the centroid, CG bolt group. Fine. So here if I take P1, this is P2. So since this is not symmetrical, if it is applied exactly at the center, you will be providing both the things, it is same. But this is not symmetrical. Load is applied somewhere here. Now, if I have to see length of the well here, length of the well here. So if it is length of the well here, length of the well here, P1 into H1 and P2 into H2. P1 into H1 and P2 into H2, where P1 is length multiplied with throat thickness. Here also this is length multiplied with throat thickness. P1 multiplied with H1, P2 multiplied with H2. So length multiplied with throat thickness. Fine. This is the length of the well multiplied with throat thickness. This is also length of the well multiplied with throat thickness. So P1 multiplied with H1 equals to P2 multiplied with H2. So that moment about center of gravity equals to 0, and total load P equals to P1 plus P2. This total load has to be taken by these two wells. At the same time, moment about center of gravity should be 0. Sir, what happens if there is moment? If there is moment, extra torsional stresses or bending stresses will be there. You have to design for that also. In order to avoid, you have to design the lens in such a way that P1 equals to moment about center of gravity equals to 0, that is P1 into H1. Anti-clockwise moment should be equals to P2 into H2, that is clockwise moment. These are the points that you have to remember. If end fillet is also used, if end fillet is also done, then what we'll be doing is total load P equals to P1 plus P2 plus P3. Total load P equals to P1 plus P2 plus P3, and moment about center of gravity equals to 0. Moment about center of gravity equals to 0. Then what we can write over here is P1 into H1 should be equals to moment about center of gravity, P1 into H1, P2 into H2. At the same time, P3 multiplied with H3. You should also consider this. So total load P equals to P1 plus P2 plus P3, and moment about center of gravity must be equal to 0. So that is P1 into H1, P2 into H2 plus P3 into H3. Sum of the moment should be equals to 0. Based on that, you will try to find out the length. This is one type of the problem. Fine. Now, once we have seen this type of connections, next I think it is eccentric connections that we have to be worried about. All those problems you have to solve. You don't have a choice. Fine. Once again, I'm just giving you the basic concepts. Basic concepts in the sense we are remembering the concepts. This is quick revision. So we are trying to remember the concepts. Fine. Next, eccentric welded connections. Eccentric welded connections. In eccentric welded connections, there is in-plane eccentric welded connections and out-of-plane eccentric welded connections. In plane eccentric welded connections, weld group and loading are in same place. So in-plane bolted connections, same thing. Loading bolt group and loads are in same plane, and here weld group and load is in same plane. Fine. Because of this, there will be direct stress and there will be bending stresses, or there will be rotational stresses, and there will be direct shear stress, and there will be, because of the torsional, there will be torsional shear stress, and total resultant would be under root of F1 square plus F2 square plus 2F1 F2 cos theta, right? Now, so radial distance will be from center of bolt group, center of weld group to the end. That is the radial distance R. So T equals to P into E. Fine. So F1, how we will calculate is total load upon the area of the bolt group. Here it is different. Here it is not number of the bolts. So it is simply total load. Total load. If let us say if this is the weld that you are we are giving the weld something like this, and if this is the channel section, center of gravity will be somewhere here. This is CG. So what you have to do exactly here is, you have to calculate this radial distance R. This is the radial distance R. So if this is the radial distance R, then there will be F1 something like this, and there will be F2 something like this. Fine. So if let us say this is F1 and this is F2, and this is F1, this is F2 radial distance. If this is theta, this is also theta. Fine. And what is F1? F1 would be equals to total load P upon area of the weld, where A equals to area of the weld. This is stress due to the direct shear stress. And torsional shear stress, F2 would be equals to PE upon sigma Ri square multiplied with Ri. Sigma R, or simply it is PE upon J multiplied with R. So J equals to polar moment of inertia, that is equals to Ixx plus Iyy. Ixx plus Iyy. If this is Xx, this one is Yy. So polar moment of inertia J equals to Ixx plus Iyy. Fine. So if this is J and T is the torsional shear, T is the torsional force. So this is P upon J multiplied with Ri. J is polar moment of inertia, Ixx plus Iyy multiplied with R is the radial distance, and resultant stress Fr. Fr would be equals to under root of F1 square plus F2 square plus 2F1 F2 cos theta. 2F1 F2 cos theta, where theta is the angle between F1 and F2. Theta is the angle between F1 and F2. Polar moment of inertia, that is Ixx plus Iyy. Fine. So this is resultant stress. This resultant stress should be less than Fs. This resultant stress should be less than Fs. Fine. Should be less than Fs. Fs equals to 110 MPa if it is WSM, and it equals to Fu upon root 3 multiplied with 1.25 if it is LSM. Fine. Torsional formula is generally applicable for circular sections only, but here it is C section. Approximately we are trying to solve. Okay, don't worry about it. Anyway, whatever the type of section, just try to find out J value and get the answer. This is how you solve for in plane eccentric connections. Next, if it is out of plane eccentric connections, so out of plane eccentric welded connections, if it is out of plane eccentric welded connections, then what exactly we are going to do? Out of plane eccentric connections, what exactly we are going to do over here is, so that is equals to, if the load is being applied over here at an eccentricity E. If load is applied at an eccentricity E, then here the weld and the loads are not in same plane. Welding is in this plane and loading is in this plane. So because of this, there will be a direct load and there will be a bending because of there will be bending moment. Due to the bending moment, so there will be horizontal shear stress. Due to bending moment, there will be horizontal shear stress in the weld, and due to direct load, there will be vertical shear stress in the weld. Fine. So idea is try to find out what is the vertical shear stress and what is the horizontal shear stress. If they ask vertical shear stress due to direct load, F1 equals to total load upon area. Shear stress due to direct load. Shear stress due to direct load. So this is A equals to area of weld, and F2 equals to bending stress due to direct load, that is M upon I multiplied with Y. M upon I multiplied with Y. Find M equals to PE upon I by Y. PE upon I by Y. So where I equals to I for this small rectangles. Collectively this would be equals to, if this is T is the throat thickness multiplied with D is the depth. Total area, if I have take this is T, this is T, this is also D. Total area would be equals to 2T times D, and I value would be equals to T multiplied with D cube upon 12 whole multiplied with 2. T multiplied with D cube upon 12 whole multiplied with 2. This is the value of I. Fine. So F2 would be this and F1 equals to that. So finally the resultant force would be equals to under root of F2 square plus 3 times F1 square. This is present LSM. You have to use something like this. This should be less than Fs. F2 square plus 3 times F1 square. F2 equals to PE upon I multiplied with Y. M upon I multiplied with Y, and F1 equals to P upon A. Shear stress due to direct load and shear stress due to bending load. This is the tensile stress or shear stress due to bending load, and this is shear stress due to direct load, P upon A, P upon I multiplied with Y. Fine. P upon I multiplied with Y. So these are the problems points that you have to remember. P upon I multiplied with Y and P upon A. So these are the points that you have to generally remember. This is eccentric welded, out of plane eccentric welded connections. We have seen in plane eccentric welded connections and out of plane eccentric welded connections. So with this, connections are completed. So once connections are completed, we have seen bolted connections and welded connections. Now the next one would be design of tension members, next design of compression members, next design of flexure members. We'll discuss that also. So this is the idea. Fine. So we are in steel quick revision, right? So in this quick revision we have seen up to strength of the lap joint. Now anyway, I took some decent amount of time for that, but right now we don't have time, so I'll try to wrap it up as soon as possible. So for that, what I'll be doing is I'll be explaining things directly from the notes. I'll not write down everything. I'll just explain the things directly from the notes. So the next would be strength of the rivet joint for double cover plate joint or butt joint, double cover butt joint. Fine. We have seen for lap joint is subjected to the single shear, whereas butt joint is subjected to the double shear. Fine. Butt joint is subjected to double shear. There are main plates. There are main plates and there are cover plates. So since figure is not clear over there, I have drawn it here. This is double cover butt joint, double cover butt joint, double cover butt joint. So if this is double cover butt joint, it is subjected to what? It is subjected to double shear here, not a single shear. Here shear over here, shear over here. If I have to draw the free body diagram of the nut or bolt, how exactly it looks like is, fine, it is subjected to double shear and bearing. So since it is subjected to double shear, if I have to talk about PS, strength of the bolts in the shear, then it is N multiplied with 2 multiplied with pi by 4 d square multiplied with Fs. Fine. The same thing as that of lap joint, but only difference is 2 times. Why 2 times? Because it is subjected to double shear. N is the number of bolts. Or rivets. D is the dia of the rivet hole. Fs is the shear strength of the bolts or rivets, that is 100 MPa if it is WSM, and Fu upon root 3 multiplied with gamma W, or 1.1 if it is 1.25 if it is LSM. Fine. So number of bolts, if they ask, it is 9, not 18. Fine. It is 9 here. This is shear strength in shear, and strength in bearing, it would be N multiplied with D multiplied with T multiplied with FB. Here the major difference being T. What is T? T is the minimum thickness of thickness of thinner plate, and sum of cover plate thickness. Thickness of thinner plate and sum of cover plate thickness. So sum of cover plate thickness and thickness of thinner plate, that is your PB. N multiplied with D multiplied with T multiplied with FB, and N multiplied with 2 into pi by 4 D square multiplied with Fs. This is PS and this is PB. Fine. And once these two things are completed, then finally that is tensile failure or tearing strength of the plate. So tensile failure or tearing strength of the plate, if they ask A-net multiplied with 0.9 Fu upon 1.25 or A gross multiplied with Fy upon 1.1 or A gross multiplied with Fy upon 1.1. So minimum of these three things, generally PT would be the minimum, so we'll be going with that. Fine. If they ask efficiency, then efficiency would be equals to, efficiency of the strength of the joint would be equals to minimum of PS, PB, PT upon strength of the solid plate. So this is efficiency of the joint, strength of the solid plate, that is the efficiency of the joint. Once this is completed, and this is how we'll try to follow it. And if they ask per gauge length, if they ask per gauge length, if they ask what is the strength of the joint per gauge length, PS would be equals to N multiplied with N1 multiplied with 2 into pi by 4 D square multiplied with Fs. N1 is the number of bolts per gauge length. N1 is the number of bolts per gauge length. If I take this as the single gauge length, So number of bolts per gauge length, that is your N1. N1 is the number of bolts per gauge length, and D is the dia of the rivet hole. So N1 equals to number of bolts per gauge length, and D is the dia of the rivet hole, and all those things, everything will remain same. And PB will also be N1 multiplied with D multiplied with T multiplied with FB, where T is the minimum of thickness of thinner plate and sum of cover plate thickness, and PT would be equals to A net multiplied with 0.9 FU upon 1.25 or AG multiplied with FY upon 1.1. This is for LSM. A net, if they ask, that would be equals to G minus D multiplied with T. That is the idea. Fine. So if they ask efficiency, minimum of these three things upon strength of solid plate, that would be your efficiency. We have already discussed what is the efficiency per gauge length. So accordingly you have to solve it. And if they ask what is the rivet value, if it is subjected to double shear, rivet value for double shear. If they ask what is the rivet value for double shear, then what exactly we'll be doing is RV equals to minimum of Fs comma Fb. So Fs is equals to Fs equals to 2 multiplied with pi by 4 d square multiplied with small fs, and Fb equals to d multiplied with t multiplied with Fb. This is Fs and this is Fb. This is minimum of these two things, Fs and Fb, that is rivet value. Fine. So these are the points that you have to generally remember, where T is the minimum of sum of minimum thickness of thinner plate and sum of cover plate thickness. Thickness of thinner plate and sum of cover plate thickness. Same thing. So that is the same thing you will be seeing over here. Main plate and cover plates. Shear strength of rivets in the joint 2 multiplied with pi by 4 d square multiplied with Fs, and bearing strength of all rivets n multiplied with d multiplied with t, where t is the sum of cover plate thickness or thickness of thinner plate. So and then strength of this one. Fine. So this is how you'll try to find out the efficiency of the joints. Next, arrangement of the rivets. Arrangement of the rivets or bolts is one of the finest, another important thing. So there are different types of arrangements that we generally see: chain riveting, diamond riveting, and staggered riveting. Fine. The most efficient one is the staggered riveting. Anyway, if we see from the starting chain riveting, the weakest position or the weakest section is this one. If this is the chain riveting, fine, I hope diagram is clear. This is the chain riveting. This is 1-1, this is 2-2. At section 1-1, if they ask what is the strength, PT, that would be equals to B minus 3D into T multiplied with FT, where N is 3, right? 3 dia holes. So 3 dia holes. This is one thing. For N equals to 3 from the above figure. And diamond riveting, this is diamond riveting. 1 bolt here, 2 bolts here, 3 bolts here. So this is diamond riveting. So if this is equals to B minus D. D is the dia of the hole multiplied with T multiplied with FT. Now here you are subtracting 3 times, whereas here you will be subtracting only 1 time. So generally diamond riveting is more efficient because the value is more. So this is more efficient than chain riveting. Diamond riveting is more efficient than chain riveting. So next, if that is the case, now we'll go to section 2.2. If I go to section 2.2, section 2.2, what is the strength? Strength at section 2.2 is B minus 3D into T into FT, plus there are 3 bolts. Fine. If failure has to occur, if cracking has to occur at 2.2, 3 bolts has to fail, then only cracking will occur at 2.2. Right? Cracking will occur at 2.2 only if these 3 bolts fails. So for that, B minus 3D into T into FT plus 3 times RV. rivet value plus 3 times RV rivet value. Okay, fine. In diamond riveting, if failure has to occur at 2, if diamond riveting failure has to occur at 2, so this is B minus 2D into T into FT plus there is a rivet value RV. If this bolt has to fail, and the strength over here is B minus 2D into T into FT, right? So from that, if these two things, so this is at 1, at 1, diamond riveting is stronger than chain riveting. At 2, diamond riveting is B minus 2D into T into FT plus RV plus and for chain riveting this is the case. Sometimes in diamond riveting this can be weakest. Why? Because there is a single bolt. Single bolt can easily fail. If it fails, then this would, here the failure can occur. Whereas in chain riveting failure will not occur because there are 3 bolts. It is more stronger. So chain riveting is weaker at section 1, it is stronger at section 2. Whereas diamond riveting is stronger at section 1 and weaker at section 2. So since this is the case, in order to make it more strength, in order to increase the strength, this type of riveting is far better. This type of riveting is far better. Fine. This type of riveting is far better. And staggered riveting is also something that we'll see in the design of tension members, but we can go for the staggered riveting, that is even more better. So according to the question, just give what you can give. That is one of the things. And we have seen the specifications. What I mean specifications is indirectly like what is the type of the rivet, and I mean pitches of the rivets and specifications for the pitch of the rivets, right? And everything else is problems, and we are not discussing the problems right now. So once the connections is complete, I mean these type of connections we have seen, next would be eccentric connections. All these things are problems. Problems are something that you have to solve from your previous year's questions, or you can solve it from right now, whatever that is, from your test series. You might have started your test series, but this is just a clear idea. Fine. Next, eccentric riveted connections. Eccentric riveted connections or bolted connections. In that first one, both bolts and loads are in same plane. So this is in plane eccentric connections. Here bolts and loading is in same plane. Bolts and loading is in the same plane. So this is the plan view. There is an I section, that is the plan view, and to the I section a gusset plate is connected to it. Fine. So gusset plate is connected to it and load is applied exactly in the plane. See, this is revision. That's why I'm going it faster. That means you have already studied this and just brushing you up. Fine. Don't think that, sir, why you're not drawing. Yeah, initially I did because I thought we have time, but we don't have time right now, so I'm going it faster, right? Fine. So keep this in the mind. In revision, it's like, you know, you'll open the book or you'll try to remember everything what exactly is present over there, right? So when I'm explaining to it, I don't have to explain the concepts in detail. I'll just giving a clear idea what are the points that you have to remember. So this is in plane eccentric connections. In plane eccentric connections means bolts and loading are in the same places or in same plane. Fine. So bolts and loading are in the same plane, and load is applied at an eccentricity from the CG of the bolts. This is bracket. Load is applied at an eccentricity from the CG of the bolts. This is front view and this one is top view. This is top view and this is front view. Now, since loading is applied over here, bolts will try to rotate. Bolts will try to rotate. So if it tries to rotate like this, that means it is subjected to a torsional stress, torsional shear stress and direct shear stress. Fine. It is subjected to torsional shear stress and direct shear stress. Fine. So from that, see, the effect would be a moment of P into E and a direct load. Due to direct load, there will be a torsional shear. Due to eccentric load moment, there will be twisting moment, and due to direct load, there will be direct shear stress. Fine. So F1 is the shear force in the rivet due to direct load that is generally given as P upon sum of the area multiplied with area of each bolt. So indirectly, if generally all bolts will be of same area, so this is P upon number of bolts. If load is 10 kilonewtons, if bolts are 4, then each one will be subjected to 2.5 kilonewtons. This is shear force due to direct load. And shear force due to this is P upon N, that is Fn. And shear force due to torsional stress, so this is torsion upon, this is generally T by J into R, where J is the polar moment of inertia, that is A into R square multiplied with R. The same thing, P into sigma Ri square multiplied with R. Simple. Fine. If area is same, it would be something like this, P upon sigma Ri square multiplied with Ri. So you know F1, you know F2, and so for maximum force, or what are the bolts that is subjected to maximum force, if they ask, just the radial distance should be more and theta between F1 and F2 should be less. Radial distance from CG of the bolt group. If I say this is the CG of the bolt group, from here the maximum radial distance will be for end bolts. Fine. And F1 will be acting downwards, F2 will be perpendicular to the line joining CG of the bolt group to the bolt under consideration. This is F2, this is the radial distance, F1 will be acting downwards, and let us say angle between F1 and F2 is theta. If they ask resultant, under root of F1 square plus F2 square plus 2F1 F2 cos theta. That would be your final force. Resultant force in the rivets. If they ask what is the resultant force in the rivets or bolts, first find out F1. F1 equals to load upon number of bolts, assuming bolts are of same area, and F2 equals to PE upon sigma Ri square multiplied with Ri. Ri is the radial distance from CG of bolt group to the bolt under consideration. If they ask maximum force, it will be for the bolts which are having R as maximum, more amount of R, and theta value should be less. If theta is less, cos theta is more, resultant will be more. So the resultant force is something like this, and this resultant force should be less than or equal to RV, rivet value. It should not be more than RV. If it is more than RV, then bolt fails. So whenever we are designing for eccentric connections, you have to design in such a way that the resultant force due to the direct load and due to the torsional load should not be more than rivet value. Fine. So RV is the rivet value, and this has to be safe. For rivet to be safe. Fine. So rivet value, it is to be safe. Resultant force under root of F1 square plus F2 square plus 2F1 F2 cos theta. F1 equals to P upon N, and F2 equals to P upon sigma Ri square multiplied with Ri. Under root of F1 square plus F2 square plus 2F1 F2 cos theta. Always remember this. Try to find out F1 and F2, and that should not be more than rivet value. This is one of the things. And everything else is problems which you have to find, do it out. Next, if we have seen in plane eccentric connections, next one is out of plane eccentric connections. So out of plane eccentric connections, how exactly you are going to find out of plane eccentric connections? Out of plane eccentric riveted connections. If I have to ask what is the out of plane eccentric riveted connections, then here bolt group is in this plane and loading is in this plane. This is in this plane and this is in this plane. That means bolts and loading groups are not in same plane. So that means here what happens is, due to the eccentricity, this is plan view. Fine. There is an I section like this, to that a gusset plate is connected and load is applied over here. Because of this load, there will be, the effect would be direct load, and there will be a bending moment on the bolts. The effect would be direct load and there will be bending moment on the bolts. So due to the bending moment, the bending stresses that is developed would be equals to PE. PE you have to find out. So due to the bending moment, it will be subjected to, top bolts will be subjected to tensile stresses, and bolts below neutral axis, we don't know, it's not subjected to anything. Why? Because compression is taken by these two plates, whatever the plates that is connected here, I section and gusset plate are connected. So compression is taken by these two things, whereas tension is taken by the topmost bolts or rivets. So tension is taken by that and compression is taken by the plates. And neutral axis will be at a depth of h by 7 from the bottom. Neutral axis will be at a depth of h by 7 from the bottom, and depth is taken from the bottom of the gusset plate to the topmost bolt or rivet. This is the depth. So if this is depth h, and neutral axis will be at a depth of h by 7 from the bottom. So bolts above this is subjected to tension, and bolts below this is not subjected to anything. Fine. Bolts above this is subjected to tension, that is because of the moment, and due to direct load there will be shearing of the bolts, shear force. So it is subjected to the shear stresses and tensile stresses. So now if this if that has to not fail, then the condition that is to be satisfied is, and the condition that should be satisfied is sigma at calculated upon sigma at plus tau Va calculated upon tau Va should not be more than 1.4. Sigma at is calculated tensile stress, sigma at is permissible tensile stress, tau Va is calculated shear stress, and tau Va is permissible shear stress. It should not be more than 1.4. So sigma at is calculated tensile stress, sigma at is permissible tensile stress, tau Va calculated is permissible shear stress, and this is calculated shear stress, and this is permissible shear stress. These are one of the points. Next, if I have to use LSM concept, PT calculated upon PT whole square plus PS calculated upon PS whole square should be less than or equal to 1. Fine. So PT calculated upon PT, PS calculated upon PS whole square should be less than or equal to 1. This is as per LSM. Calculated tensile force upon permissible tensile force, and calculated shear force upon permissible shear force. So sir, what I have to use right now? Maximum. Right now you will be using LSM only, and in the problem if they have asked use WSM, then you will be using the above criteria. That is sigma at calculated upon sigma at plus sigma tau Va calculated upon tau Va should not be more than 1.4. PT calculated upon PT whole square plus PS calculated upon PS whole square should be less than or equal to 1. Calculated factor tensile force and calculated factor shear force. So these are the points that you have to generally remember. So PT calculated upon PT plus PS calculated upon PS should not be more than 1.4. Fine. So with this, connections are completed. In connections, the major thing in the bolts that you have to remember is specifications, strength of the butt joint, strength of the lap joint, strength of butt joint, and then design of and eccentric connections, in plane eccentric connections, out of plane eccentric connections. These are the major things that you have to remember. Fine. So next part in our revision series is, the next chapter would be connections. This is steel revision. We are still doing steel revision only. So next one is connections. In connections, the different types of connections would be bolts. The different types of connections would be bolts and welds, right? So bolts and welded connections. Bolts and welded connections. So in this session we'll see what exactly is the bolted connections. In the next session we'll see how exactly the welded connections would be. Fine. So bolted connections, if I take simple example, if I have to show the different namings in the bolted connections. Let us say this is a plan view. Fine. If this is the plan view, load is being applied like this, and let us say load is being applied like this. This is P, this is also P, some load, or I'll write load is F. Load is F. Fine. So distance between the consecutive bolts in the direction of application of the load. Distance between two consecutive bolts in the direction of application of the load is called as distance between two consecutive bolts in the direction of application of the load is called as pitch. Distance between two consecutive bolts in direction of application of load is called as, this is pitch. And distance between two consecutive bolts in the direction perpendicular to the application of the load, the direction perpendicular to the application of the load is called as gauge. This is gauge distance. Fine. And distance between the end of the plate and to the last bolt in the direction of application of the bolt is called as end distance. This is end distance. Fine. And this one is called as, in the direction distance between the end of the plate or edge of the plate to the last bolt in the direction perpendicular to the application of the force, this is called as edge distances. This is called as edge distance. These are the first nomenclature you should know. This is P, that is pitch distance. Pitch distance. Fine. And this one is gauge distance. Gauge distance. Pitch is the distance between successive bolts in the direction of application of the load, and distance between successive bolts in the direction perpendicular to the application of the load is called as gauge distance, and distance from the edge of the plate to the last bolt is called as end distance, and distance from the edge of the plate to the last bolt is called as edge distance. So these are the points that you should generally remember in pitch distance minimum concept. Fine. Now if we have to see the specifications of the pitch. Specifications of the pitch. Specifications of the pitch distance. Specifications of the pitch distances. See, generally we can use bolt or rivets. Fine. What exactly is difference between bolts and rivets is, bolts, you generally see that bolts, there will be nut and a bolt, right? That is bolts. Rivets would be, you will heat that rivets. You will heat the rivets. That means it would be something like this. Fine. This is rivets. This is rivets. This is generally called as shank dia. Shank dia. Anyway, what exactly happens is, you'll heat it, you'll put it, you'll heat it, and you'll put that in the holes, and you'll cool it. Once you cool it, it expands and it gets fixed. In a plate, you'll make a hole. Fine. And then you'll heat the rivet. You'll put the rivet in that hole, and then you'll allow it to cool itself. If you allow it to cool itself, then what happens? It gets cool and it gets fixed to the plate. Fine. So this is one of the things. Specifications of the pitch. Fine. So this is called rivets. So sometimes you'll be seeing bolts, sometimes you'll be seeing the rivets. Fine. So gross dia of the rivets, if I say, generally if I say gross dia of the rivets, generally this hole, there will be rivet and rivet hole. Rivet hole will be more than that of the rivet dia. Fine. So gross dia of the rivets, gross dia of the rivets, gross dia of the rivets, gross dia of the rivets equals to 5 plus 1.5 if phi is less than or equal to 25 mm, where phi is the nominal dia of the rivets. Nominal dia of rivets. Phi is nominal dia of rivets. This is gross dia of rivets or gross dia of, or you can also say this as dia of hole. Dia of rivet hole. Dia of rivet hole. And the same thing is equals to 5 plus 2 mm if phi is greater than 25 mm. 5 plus 2 mm if phi is greater than 25 mm. These are specifications of the pitch. Specifications of the pitch: gross dia of the rivets or dia of rivet hole equals to 5 plus 1.5 or 5 plus 2. Phi is less than or equal to 25 mm and phi greater than 25 mm. Fine. These are the points that you should generally remember. Fine. Now coming to the minimum pitch of the rivets. Minimum pitch of the rivets. Minimum pitch of the rivets equals to 2.5 times nominal dia of bolts. 2.5 times nominal dia of bolts or rivets. 2.5 times nominal dia of bolts or rivets. Nominal dia 20 mm, gross dia would be 20 plus 1.5 mm. So this is the minimum pitch that you should generally provide. Fine. And minimum end or edge distance. Minimum end or edge distance. Minimum end or edge distance would be equals to 1.5 times gross dia of the rivets. You can use this right now, gross dia, not nominal dia, gross dia of the rivets. Minimum end or edge distance is 1.5 times gross dia of the rivets. Fine. Sir, why minimum end distance or edge distance should be provided? It is generally provided to avoid shearing failure, bearing failure and splitting failure of the plates. We will see the types of failure when we are discussing, but this is the minimum end or edge distance that you should provide. Fine. So maximum pitch for rivets under compression. For rivets under compression. Maximum pitch for rivets under compression. Maximum pitch for rivets under compression equals to minimum of 12T or 200 mm. 12T or 200 mm, where T equals to thickness of thinner plate. T equals to thickness of thinner plate, where T equals to thickness of thinner plate. Maximum pitch for rivets under compression equals to minimum of 12T or 200 mm, where T equals to thickness of thinner plate. Why, sir? Why that maximum pitch is provided? This maximum pitch is provided in order to avoid buckling. So pitch should not be more than 12T or 200 mm, whichever is less. Fine. So what happens if you are providing more pitch? Then what happens is the the member between these two bolts, there is possibility of buckling. What I am saying, member subjected to compression, right? Here the member is subjected to compression. So in order to avoid buckling, pitch should not be more than 12T or 200 mm. Fine. In order to avoid buckling between the bolts. Fine. The same thing if If members are subjected to tension, maximum pitch between the rivets. If members are subjected to tension, maximum pitch for rivets under tension. Maximum pitch for rivets under tension. Maximum pitch for rivets under tension equals to minimum of 16T or 200 mm. Minimum of 16T or 200 mm. This is why if pitch is more, what happens is splitting of failure, splitting between the plates can occur. If pitch is more, then what happens is splits. There is possibility of this type of splitting. Splitting between the plates can occur, that also leads to the failure. So in order to avoid this, the different criteria for pitches is something like this. This is maximum pitch for rivets under compression, maximum pitch for rivets under tension. Fine. So these are the things. Now the next point would be here pitch should not be more than 16T or 200 mm. If rivets are staggered riveting, if rivets are staggered riveting, rivets provided are staggered riveting, so what is staggered riveting, what is chain riveting, what is diamond riveting, we'll discuss that later. But anyway, if let us say rivets provided are staggered riveting and G is not more than 75 mm, G gauge distance is not more than 75 mm, and let us say this is staggered riveting. Okay, this is staggered riveting. So if there is staggered riveting and G is not more than 75 mm, then above values can be increased by 50%. Now, so what exactly this means is, I have given some specifications over here. Fine. So if rivets are staggered, and G not more than 75 mm, then above values can be increased by 50%. That means maximum pitch of rivets under compression, equals to minimum of 12 into 1.5, that is 18T or 300 mm. Fine. And maximum pitch of rivets under tension, maximum pitch of rivets under tension equals to minimum of 24T or 300 mm. 16 into 1.5 is 24. So 24T or 300 mm, maximum pitch of rivets under compression equals to minimum of 18T or 300 mm, minimum of 24T or 300 mm. Fine. So these are the points that you should generally remember. If rivets are staggered, then these values can be increased by 50%. Fine. So if you remember these points, next Next, maximum pitch of tack rivets. Maximum pitch of tack rivets. Maximum pitch of tack rivets. Maximum pitch of tack rivets is generally given as minimum of 32T or 300 mm. 32T or 300 mm. What exactly is tack rivets? If we are talking about tack rivets, what exactly is tack rivets? Generally, there are two types of rivets: structural rivets and tack rivets. Fine. So, tack rivets are the type of rivets which does not carry any load, but it will make sure that different elements acts as a single unit. Let us say this is a gusset plate. This is a gusset plate, and this is one angle section. Behind this there is another angle section. Just say that. That means if this is the front view I am showing you, this is the front view. Front view. How exactly the back view would be? Top view. Fine, not back view, this is top view. Fine. So there will be some type of rivets that, let us say there will be some structural rivets. These are structural rivets. Fine. So that means there will be, let us say, some 4 rows of rivets. These rivets are called as structural rivets. Why? Because these takes loads. These rivets are called as structural rivets because these takes load. And there is one angle here. Behind this there is another angle. So if behind this there is another angle, there will be these are called as tack rivets. Tack rivets. These type of rivets are called as tack rivets. Fine. So tack rivets, what exactly happens is, it will not take any load. It will not take any load. It just makes sure that both the things acts as a single unit. Fine. So this is tack rivets. It will not take any load and it will make sure that everything acts like two angles will act like a single unit. So these are structural rivets that takes load. It takes load. It takes load, whereas tack rivets makes sure that different members acts like a single unit. Make sure that different members acts like a single unit. Different members acts as a single unit. Right? This is your top view and that is your front view. This is the top view and this is your front view. So that means you'll see that one angle here, behind this there is another angle, both the things are connected by tack rivets. This is the pitch, and it should not be greater than minimum of 32T or 300 mm. Fine. And fine, this is one of the criteria. Now let us see if this member is subjected to tension. If this member is subjected to tension, then maximum pitch of tack rivets, this is subjected to tensile force, maximum pitch of tack rivets should not be more than 1000 mm. Should not be more than 1000 mm. Maximum pitch of tack rivets for the members subjected to tension should not be more than 1000 mm, and for members subjected to compression, maximum pitch of tack rivets for the members subjected to compression, maximum pitch of tack rivets for members subjected to compression, maximum pitch of tack rivets for members subjected to compression, P should not be more than 600 mm. This is one of the point. Fine. Maximum pitch of tack rivets for members subjected to tension is 1000 mm, and for members subjected to compression, maximum pitch of tack rivets, for members under tension, equals to 1000 mm. Maximum pitch of tack rivets for members under compression, maximum pitch of tack rivets for members under compression, equals to 600 mm. Fine. Maximum pitch of tack rivets for members under tension equals to 1000 mm. Maximum pitch of tack rivets for members under compression equals to 600 mm. Fine. So these are the points that you should generally remember. Some of the basic points. Now the other type of thing over here is types of joints. Fine. So in types of joints, the first one would be lap joint. Let us say this is load is being applied like this. Fine. This type of joint is called as lap joint. This type of joint is called as lap joint. Fine. So if this is lap joint, when load is being applied like this, what exactly, this is one least efficient joint. So if this is one of the least efficient joint, then if this is one of the least efficient joint, why? Because the line of action of forces is not same. line of action of forces is not same. So they apart from shearing stresses, here there will be some amount of shearing, right? There will be shearing. Apart from shearing stresses, apart from shearing, there will be bending. There will be bending shear stresses also, because these are like two equal and opposite forces subjected to some couple, subjected to a couple. Why? Because two equal and opposite forces separated by a distance of length L, so it tends to form a couple. There will be bending stresses in it. In order to avoid this bending stresses, generally grip length should not be more than 5 times dia. This will be your grip length. Grip length should not be more than 5 times dia. Grip length should not be more than 5 times dia. So lap joint, least efficient joint, least efficient joint, least efficient joint members are subjected to extra bending stresses. Extra bending stresses. Members are subjected to extra bending stresses. Least efficient joint and members are subjected to extra bending stresses. Apart from the shear stresses, there will be extra bending stresses. In order to avoid bending, grip length, LG is called as grip length, should not be more than 5 times nominal dia of the bolts. Fine. If LG is not more than 5 times dia, there will not be any bending stresses. There will not be any effect of bending stresses. There will not be any effect of bending stresses. There will not be any effect of bending stresses. This is lap joint. This is one of the least efficient joint. Why? Because apart from shear stresses, there will be bending stresses also. Fine. Next, single cover butt joint. Single cover butt joint. Here the line of action of forces is same. Line of action of forces is same, but joint is not symmetrical. Joint is not symmetrical. So line of action of forces is same here. Line of action of forces is same here, but the joint is not symmetrical. Since joint is not symmetrical and line of action of forces is not same, this is efficient than lap joint but not most efficient joint. Fine. So here efficient than lap joint. Efficient than lap joint. Line of action of force is same. Line of action of force is same but joint is not symmetrical. But joint is not symmetrical. Line of action of force is same but joint is not symmetrical. That is single cover butt joint. Next one, double cover butt joint. Double cover butt joint. Double cover butt joint. So if we are talking about double cover butt joint, how exactly that looks like is, this is one of the most efficient joint. Why? Because the line of action of forces will be same, at the same time joint is symmetrical. Line of action of forces is same and joint is symmetrical. There will be only shear stresses, there will not be any extra bending stresses in this. Line of action of forces is same, at the same time joint is symmetrical. Fine. So line of action of force is same and joint is symmetrical, so there will not be any extra bending stresses. So this is one of the most efficient joint. Most efficient joint. So if this is one of the most efficient joint, double cover butt joint, one of the most efficient joint, because line of action of forces is same and line of action of forces is same and member is symmetrical. There will not be any bending stresses, there will not be extra bending stresses, there will be only shears, there will be only shearing of the bolts or different types of normal failure will be there, but there will not be any extra bending stresses. So lap joint is least efficient joint, butt joint is most efficient joint. Now types of failures in the joints. If you see types of failures, fine. So in types of failures, the failures that are avoided is shear failure of plate, shear failure splitting failure, and bearing failure. Bearing failure of plates can be avoided, by providing proper end, or edge distance. By providing proper end or edge distance, shear failure of the plates I am talking, shear failure of the plates, splitting failure of the plates, bearing failure of the plates can be avoided. How exactly you can look at this is, this is shear failure of the plate. Fine. So that means here the failure will occur, not bolt, shear failure of plate. If you provide sufficient end distance, if there is more amount of end distance, this type of failure can be avoided. Next is splitting failure. That means plate is getting split like this. This is also splitting failure. That means plate is, if plates are connected like this, let us say, if plates are connected like this plate is going out of shape like this. It goes out of shape like this. So splitting failure of the plates, that also can be avoided. If this distance is more, splitting failure also can be avoided. That is generally because of the distortion type of things. Fine. Next is bearing failure of the plate. Bearing means plate going out of shape. That means just take an eraser, put a pin in it. Take an eraser, put a pin in it, and if you pull eraser, what happens is pin will be straight, but eraser will go out of shape. Fine. Bearing means plate going out of shape. This is bearing failure of plates. Bearing failure of plates. This is splitting failure of plates, and this is shear failure of plates. So these failures can be avoided by providing proper end or edge distances. So by providing proper end or edge distances, these type of failures can be avoided. Okay. Next, now if you can avoid this, then what we generally design for? We generally design for tearing failure or tensile failure of the plates. So in failure of plates, we generally design for tensile failure of plates. This is tearing failure or tensile failure of plates. So tearing failure or tensile failure of plates. Tearing failure or tensile failure of plates, we generally design for that, tearing failure or tensile failure of plates. Fine. So this is one of the problem, tearing failure or tensile failure of the plates. We design for so let us say this is third one, tensile or tearing failure of plates, tensile or tearing failure of plates. And if you see the failure in the bolts, if you have to see failure in the bolts, if I take this as some load, then what happens is at this one, bolts can shear off. That is shearing failure of bolts. That is one thing. Next, because of application of the load, there is a huge amount of force on this. There would be a huge amount of force on this. Because of that, the bolt can go out of shape. Fine. So here there will be shearing failure of bolts. Shear failure of bolts. And this is bearing failure of bolts. Bearing failure of bolts. So we designed for shearing failure of bolts and bearing failure of bolts. This is another point that you have to remember. So we designed for shearing failure of bolts, shear failure of bolts or rivets, and this one is bearing failure of bolts, or rivets. Shear failure of bolts or rivets, bearing failure of bolts or rivets, and next one is tearing or tensile failure of bolts or rivets. So and which type of failure is more better, whether bolt failure is better, or tensile plate failure is better. Fine. If you take a connection, let us say there is a gusset plate. All these plates I'll say is connected by a single bolt. Okay, there are 3 plates that is connected to a single bolt. If this bolt fails, bolt cost is less, but if this bolt fails, so it can fail because of shear or can fail because of bearing. So if this bolt fails, whole connection fails. That means all 3 plates fails, everything fails. Or let us say if this plate fails, then what happens? I'll remove this plate and I'll put a new plate over here. Fine. So plate failure is always preferred. Plate failure is always preferred over bolt failure. Fine. So if bolt fails, total connection fails, whereas if plate fails, you can remove that plate and you can add a new plate over there. Fine. That is one of the thing. That is one of the most important thing. Fine. Shear failure of plates, bearing failure of shear failure of bolts or rivets, bearing failure of bolts or rivets. And if generally shear strength is given as PS, shear bearing strength of bolts is given as PB, and tearing strength of bolts is given, tearing strength of plate is given as PT. Now if you go for design of different types of joints, lap joint or butt joint. First I'll say this is the lap joint. Fine. Lap joint. Design of lap joint. Design of lap joint. Fine. So if this is design of lap joint, in this bolts are subjected to single shear. In lap joint, bolts are subjected to single shear. Fine. If let us say this is the lap joint, in the lap joint, bolts are subjected to single shear. Fine. Here there will be some shearing, and here there will be some bearing. So how will you calculate shear strength of the plate? Fine. So shear strength, now not plate, shear strength of the bolt. Shear strength of the bolt. Shear strength of the bolt. See, if you have to draw the free body diagram of the bolts, how exactly it would be? It would be something like this. If I take FBD of the bolt, there will be P like this, and there will be P like this. P. So there will be shear force of P acting like this. This is P, this is also P. This is the bearing and this is shearing. So if I have to see shear strength of the bolt, PS, shear strength of the bolt PS is generally given as N multiplied with pi by 4 d square area multiplied with Fs. N multiplied with pi by 4 d square multiplied with Fs, where N is the number of bolts, and D is the gross dia of the rivets, not nominal dia, gross dia of the rivets, Fs is permissible shear stress of rivets. Permissible shear stress of rivets, that is generally given as 100 MPa, 100 Newton per mm square in WSM. If nothing is mentioned in the question, you will be taking it as 100 MPa, and this value equals to Fu upon root 3 multiplied with 1.25. This is in LSM. So Fu is the ultimate stress, whereas 100 MPa, that is generally given in WSM. This is Fs value, shear strength of the bolts or rivets. Shear strength of the bolts or rivets. Next one is bearing strength of bolts or rivets. Bearing strength of bolts or rivets. Bearing strength of bolts or rivets. If we are talking about that, bearing strength of bolts or rivets, PB. Bearing strength of bolts or rivets, PB. So how exactly you are going to find that out is, if let us say this is dia D, diameter D, and this is thickness. T is the thickness of the plate directly, right? Approximately this is the thickness of the plate, and this is D is the dia of the bolt. So load will be equal to area multiplied with stress. Area is D multiplied with T, thickness of the plate, right? This area, if you see, of course this is a circular. If you see the projection, that would be a rectangle. Just see the projection will be a rectangle of dia D, thickness is T. So if we want to calculate this one, PB equals to N is the number of bolts multiplied with D multiplied with T multiplied with FB. See, in the code you will see a different formula, but since from the exam point of view I am giving you directly something like this. Fine. So N is the number of bolts, and D is the dia, gross dia of the bolts. D equals to gross dia of the bolts, and T equals to minimum thickness of the plate, thickness of thinner plate, and FB equals to permissible bearing stress of rivet or bolts. Permissible bearing stress of rivets or bolts. This is equals to 300 MPa as per WSM. 300 MPa as per WSM. This is bearing strength of bolts or rivets. PB equals to N multiplied with D multiplied with T multiplied with FB, where FB equals to something like this: permissible bearing stress of rivets or bolts, and thickness of thinner plate, gross dia of the rivets or bolts, number of bolts or rivets. This is how we will try to find out, and in LSM also value will be given to you. What is the bearing stress value? Fine. Okay. Now minimum of these two things. If they ask what is a rivet value, or fine, leave this. We will talk about rivet value later. Fine. This is bearing strength of the bolts. Next, tensile strength or tearing strength of plate. Tensile strength or tearing strength. Tensile strength or tearing strength of plate. If I have to talk about tensile strength or tearing strength of the plate, that is generally given as PT would be equals to B minus ND into T multiplied with FT. Fine. This is net area cracking. Net area cracking. So that means failure will occur at this location. Let us say this is 1, 1, and width of the plate is generally taken as B. Width of the plate is generally taken as B, and number of bolts over here is 3. So B minus ND into T multiplied with FT. Right? So B minus ND into T multiplied with FT, where B equals to width of the plate, and N is the number of bolts or rivets. Fine. And D equals to dia of rivet hole, and T is the thickness of thinner plate, and FT equals to permissible tensile stress of plate. That is generally given as 0.6 times Fy. 25/6 150, so 150 MPa as per WSM. This is as per WSM. Tensile failure of the plates. Net area cracking is what you will be considering over here. Now if you see gross area yielding, this is net area cracking. Next one is gross area yielding. Permissible tensile stress of the plate 0.6 times Fy, that is 150 MPa as per WSM. Next one is gross area yielding. So if you see as per WSM, PT would be equals to the gross area multiplied with Fy upon 1.1. This is gross area yielding. Gross area yielding as per WSM, and this is equals to upon 1.25. This is net area. This is not as per WSM, this is as per LSM. As per LSM, fine. This is net area cracking. This is also as per LSM. Fine. So PT would be minimum of these two things. Gross area yielding means here yielding will cracking will occur, and here yielding can occur. If I take this as 2, 2, here gross area yielding can occur. Gross area yielding, and here net area cracking can occur. Net area cracking. Fine. So net area cracking can occur here. Gross area yielding can occur over there. Fine. So gross area yielding can occur over there. Minimum of these two things is taken as tensile strength of the plate as per LSM, and as per WSM it is simply net area cracking. This is the only thing that you will be taking. Fine. So now what is the strength of the plate? Strength of the connection. If they ask strength of the connection, strength of the connection equals to minimum of PS, PB, PT, and we'll make sure that you can take a note. We'll make sure that PT is less than or equal to PS and PB. PT is less than or equal to PS and PB, so that if at all failure occurs, failure occur in the bolts, failure will occur in the plate but not in the bolt. Fine. And if they ask what is the efficiency of the joint, efficiency of the joint eta would be equals to minimum of PS, PB, PT upon strength of solid plate. Upon strength of solid plate. So that would be equals to, minimum would be PT only. PT is B minus ND into T multiplied with FT upon B multiplied with T multiplied with FT. So efficiency of the joint or connection is generally given as B minus ND upon B. This is the efficiency of the joint or connection, efficiency of lab joint. Fine. So this is how you are going to find out strength of the joint. Sometimes if they ask strength of the joint per gauge length, strength of the joint per gauge length, per GTH, strength of the joint per gauge length. If they ask what is the strength of the joint per gauge length, let us say this is G per gauge length. So gauge length you said between these two things or from this center to this center, this is a gauge length only. Fine. So per gauge length, if we ask PS, what would be the shear strength of the bolts? Shear strength of the bolts PS would be equals to N1 multiplied with pi by 4 d square multiplied with Fs, where N1 equals to number of bolts in gauge length, and PB would also be equals to N1 multiplied with D into T multiplied with FB, where N1 is the number of bolts in gauge length, Fine, this is one thing. Next, if this is PS, PB, next PT, how will you calculate? G minus D into T multiplied with FT. G minus D into T into FT, right? So G minus D into T multiplied with FT. G minus D, if you see per gauge length, I am talking per gauge length here. So in this gauge length, how many bolts are there? Only one bolt hole is there. So G minus D multiplied with T multiplied with FT. Fine. So that would be one of the things. G minus D multiplied with T multiplied with FT. This is PT. G minus D into T multiplied with FT, where FT is the permissible tensile stress of the plate. Strength of the joint per gauge length we have seen, and if they ask efficiency of joint per gauge length, efficiency of joint per gauge length, if they ask, that would be simply G minus D into T multiplied with FT upon G multiplied with T multiplied with FT. So these values would be equals to G minus D upon G. This is efficiency of the joint per gauge length, that is G minus D upon G. And we have seen what is PS, PB, PT. This is per gauge length. Efficiency of the joint per gauge length, it can be different from efficiency of the total joint, both the things can be different. Fine. So in the examination, whatever they asked, accordingly you have to solve. Next one in the same thing is a rivet value. That means indirectly strength of single bolt. Rivet value RV, that is meaning strength of single bolt. Rivet value RV equals to strength of single bolt. So RV equals to minimum of Fs comma Fb. Fine. What is SF? Fs, shear strength of single bolt. Fs would be equals to shear strength of single bolt or rivet. Or bolt. That is generally given as pi by 4 d square multiplied with Fs. We know value of Fs. Next, Fb. Fb would be equals to bearing strength of single rivet or bolts. Bearing strength of single rivet or bolts, that would be equals to D multiplied with T multiplied with Fb. So minimum of these two things will be your rivet value. And once if you know rivet value, if they ask what is the number of rivets required, number of rivets would be equals to minimum of PS, PB, PT, or if force is given to you, that means this much amount of force is applied over there, then you will take that force. Okay, so upon rivet value, or if a force is applied, let us say P upon RB, where P is the applied force. Anything If force is not applied, then indirectly you try to find out the strength of the joint, and for that you will be providing the rivets. So minimum of these three things upon rivet value will be your rivets, number of rivets. Okay, so this is how we'll try to find out number of rivets for lap joint. Fine. Okay, so with this I'm closing this session. In the next session we'll see how exactly you have to calculate for double cover butt joint, and then we'll see eccentric connections, we'll see different types of rivetings. Okay, this is quick revision number 5. Quick revision of steel structures, 5th video I think. Yeah. Quick revision of steel 5. Quick revision of steel 5. Okay, so quick revision of steel video 5. So till now we have seen what is the plastic analysis in beams, how for different beams, how to find out the collapse loads on different cases, how to find out the collapse loads. We have seen that. Now we will be seeing plastic analysis in frames. Plastic analysis in frames. Plastic analysis in frames. Plastic analysis in frames. So when we are dealing with plastic analysis in frames, if we are dealing with plastic analysis in frames, so in that fine. So if you see that W, let us say A, B, C, D. Fine. So the different types of failure mechanisms that you will see is first one is a beam mechanism, right? We'll see beam mechanism in this. So beam mechanism. In beam mechanisms, it can be of different types. A separate beam or separate column is failing, that is considered as beam mechanism. This is failure mechanism. This is also beam mechanism. If a single column and single beam fails separately, that is considered as beam mechanism. Fine. So this is beam mechanism. This is beam mechanism. This is one of the independent mechanisms. So failure loads from beam mechanism you have to calculate. Once beam mechanism, if you have seen, next one is sway mechanism. Sway mechanism. Fine. So in sway mechanism, what exactly you will be seeing is, if there is horizontal loads or if frame is not symmetrical, then we generally see sway mechanisms, right? So sway mechanism, because of the application of the load, the plastic hinges will be forming somewhere at different locations. This is sway mechanism. Fine. This is sway mechanism, and combined beam mechanisms and sway mechanisms are considered as independent mechanisms. You can take the note. Beam mechanism and sway mechanism. Beam mechanism and sway mechanism are called as independent mechanism. Beam mechanism and sway mechanism. Sway mechanism are called as independent mechanism, or called as independent mechanism. Fine. Next one is combined mechanism, combined beam and sway mechanism. Combined mechanism. So combined beam and sway mechanism. When we are trying to see combined beam and sway mechanism, this is combined beam and sway mechanism, that is combined mechanisms. Failure load can also be occur over here. So whenever you're doing the analysis, you have to consider all these three analysis: beam mechanism, sway mechanism, and combined mechanism. Failure load, minimum failure collapse load, because of these three mechanisms, minimum of all these three things is considered as collapse load. Fine. So this is combined mechanism. Next one is, there are other types of mechanisms. Gable mechanism. Fine, that is also we generally see. Because of application of the load, it tries to bend in this direction. Both columns going in opposite direction is considered as gable mechanism. Gable mechanism. Gable mechanism. Fine. So these are the different types of failure mechanisms that we generally see in the frames. Fine. Now, beam mechanism, sway mechanism, and combined mechanism. Whenever a problem is given to you, you have to check all these mechanisms, and collapse load in minimum of all these three things would be your true collapse load. Fine. Next point would be number of independent mechanisms. If in the examination they are asking what are the number of independent mechanisms, number of independent mechanisms, K is generally given as number of locations plastic hinges can be formed, number of locations where plastic hinges can be formed, number of locations where plastic hinges can be formed, minus ds, number of locations where plastic hinges can be formed minus ds. So if we are taking any frame, a number of locations where plastic hinges can be formed, if they ask, let us say this is A, B, C, D, and it is subjected to the loading, something like this. So the number of locations where plastic hinges can be formed is 1, 2, 3, 4, 5. 5 locations where plastic hinges can be formed. This is generally given as N. N is 5 minus ds. That means cut the structure. How you are going to find out the ds for a frame? So ds equals to 3 times c, where c is the cuts required so that each and every member will act like a stable cantilever, or 3c minus number of reactions required to be added to make it stable cantilever, to make it stable cantilever. To make it stable cantilever. Fine. So 3C minus number of reactions required to be added to make it stable cantilever. Fine. So the number of cuts, one cut. So this will act separately as a cantilever only. This will act separately as a cantilever. Both ends are fixed. So ds equals to 3 into 1 minus 0. So ds equals to 3. So this is 3. Number of independent mechanisms is 2. Number of independent mechanisms is given as 2. Fine. What are those two mechanisms? Beam mechanism and sway mechanism. Beam mechanism and sway mechanism. Beam mechanism and sway mechanism. Okay. The next point in this is, let's solve a problem so that you'll be getting a clear idea of how to do the plastic analysis in the frames. Fine. So the problem goes, just an example problem I am taking over here. There is a load W here, length L. I'll take this as load W, length L. A, B, C, D. Fine. Always remember, if there is any horizontal load, or if member is not symmetrical, if frame is not symmetrical, then only there will be sway and combined mechanisms. If frame is symmetrical and if there are no horizontal loads, then there will not be any sway mechanisms or combined mechanisms. So if frame is symmetrical, next point is, if frame is symmetrical, you can take the note here. If frame is symmetrical, if frame is symmetrical, and there are no horizontal loads, frame is symmetrical and there are no horizontal loads, then if frame is symmetrical and there are no horizontal loads, then there will be neither sway mechanism, then there will be only beam mechanism. Okay, we can write it like this. There will be only beam mechanism, no sway and combined mechanisms. Fine. So let's see an example over here. If a problem is given to you like this and he is asking what is the collapse load. So how you are going to find out? First, check for beam mechanism. We'll check for beam mechanism. Beam mechanism can occur only in the beam BC. Okay. So beam mechanism. So beam mechanism, plastic hinges will be forming exactly at the center. It will form something like this. Fine. This is L, this is L, this is theta, this is also theta, B, E, C. This is W. Here the moment developed is anti-clockwise moment MP. Here the moment developed is anti-clockwise moment MP. Here the moment developed is anti-clockwise moment MP. And this is theta. This is also theta. Fine. Here the moment developed is clockwise moment. Fine. So apply the principle of virtual work over here. Applying principle of virtual work, what we can write down is applying principle of virtual work, external work done equals to internal work done, external work done equals to internal work done, external work done equals to internal work done. So external work done is W multiplied with, this is L times theta, W multiplied with L theta, W multiplied with L theta equals to MP times theta plus MP times theta plus theta plus MP times theta. Fine. So W would be equals to 224. So this is equals to 4 MP upon L. Right. So W equals to 4 MP upon L. This is one point. W equals to MP, MP times 2 theta plus MP times theta, 4 MP times theta. So W equals to 4 MP upon L. W is 4 MP upon L. This is one point. Beam mechanism. W is 4 MP upon L. Applying principle of virtual work, external work done equals to internal work done, W equals to 4 MP upon L. Beam mechanism. Next one is sway mechanism. So if you see sway mechanism, so in sway mechanism, if you are going by sway mechanism, then what you can write over here is sway mechanism will be something like this. Let us say if you are applying a horizontal load, you are applying a horizontal load over here. Number of plastic hinges that is to be formed, DS. Fine. Number of plastic hinges required to be formed. So DS equals to R minus S. Number of reactions would be equals to number of reactions that is to be formed. Number of reactions to be formed. Number of reactions are, or instead of this, this is the frame, right? In frame, how you are going to find out DS? DS equals to 3C minus number of reactions. Number of reactions required, number of reactions required to make it stable cantilever, to make it stable cantilever. Fine. So DS equals to 3 into number of cuts is 1, number of cuts that is required is 1. Fine. 3C. And number of reactions you have to add nothing, because here it is fixed, here also it is fixed. So 3 into 1 minus 0. So DS would be equals to 3. And number of hinges required to convert this into mechanism. Number of hinges required to convert this into mechanism is DS plus 1. That equals to 3 plus 1. That equals to 4. So number of hinges required is 4. 4 hinges has to be formed. So what are those locations? If you are considering only sway mechanism, the 4 hinges will form at A, B, C, D. 4 hinges will form at A, B, C, D. So these are the locations where hinges will form, and this is theta, this is L, this is also theta, and this one is also L. This is L theta, this is also L theta. Fine. So if this is L theta, this is L theta, anti-clockwise, here also anti-clockwise moment is developed, here also anti-clockwise moment will be developed. Fine. MP, 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 MP. Fine. So if you are applying the principle of virtual work, this the load that is applied is W. So W multiplied with distance traveled in this direction is L times theta. So applying principle of virtual work, 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 external work done equals to internal work done. External work done equals to internal work done. External work done equals to internal work done. So that is W times L theta equals to MP times theta plus MP times theta plus MP times theta plus MP times theta. So W would be equals to 4 MP upon L. W equals to 4 MP upon L. Fine. So this is collapse load due to sway mechanism. Collapse load due to sway mechanism. Fine. So if this is collapse load due to sway mechanism, that is collapse load due to beam mechanism. Now next we have to see is combined mechanism. Combined mechanism. Combined beam and sway mechanism. Combined mechanism. Combined mechanism. Fine. So in combined mechanism, what you can write over there is A, B, C, D, E. DS is how much? DS will be same, that is 3. And number of hinges required to be formed is to convert this into mechanism. Number of hinges required to convert it into mechanism. Number of hinges required to convert it into mechanism. Number of hinges required to convert it into mechanism equals to ds plus 1, that equals to 3 plus 1, that equals to 4. So ds would be equals to 4. Number of hinges required to be formed is 4. So what are those locations? A, B, C, D, E. These are these 5 locations. In this 5, generally it will not form at B. Why it will not form at B? Because the collective effect of beam mechanism and sway mechanism, moment at B would be less. Moment at C would be more. In detail was explained in the class. I am just giving the locations. It will form at A, E, C, D. So the plastic hinges will be forming at A, E, C, D. Right? So the bent structure would be something like this. Number of hinges required, to convert it into mechanism. Number of hinges required to convert it into mechanism. Number of hinges required to convert it into mechanism equals to ds plus 1, that is 3 plus 1, that equals to 4. 3 plus 1, that equals to 4. That equals to 4. Fine. So these are the locations where plastic hinges are formed. 1, 2, 3, 4. So these are the locations where plastic hinges are formed. If this is theta, this is also theta, this is also theta, and this is also theta. Here it is MP, here it is MP, here also it is MP, here also it would be MP, here also it is MP, and here also it would be MP. And W times this is L theta, this distance, and this distance will also be L times theta. Fine. So if I apply principle of virtual work, applying principle of virtual work, applying principle of virtual work, applying principle of virtual work, external work done equals to external work done equals to internal work done. External work done equals to internal work done. Fine. So external work done equals to internal work done, W times L theta plus W times L theta, that is equals to internal work done MP times theta plus MP times theta plus theta plus MP times theta plus theta plus MP times theta. Fine. This is at C, this is at D, this is at B, not B, at E, and this is at A. Fine. So W times 2L into theta equals to 2 plus 2 4 plus 2 6 MP theta. W would be equals to 3 MP upon L. So now if you see the combined mechanism, the collapse load is 3 MP upon L. In combined mechanism, collapse load is 3 MP upon L. In sway mechanism, collapse load is 4 MP upon L. In beam mechanism, collapse load is 4 MP upon L. So the true collapse load equals to minimum of these three things. So true collapse load W equals to 3 MP upon L. True collapse load W equals to 3 MP upon L. Fine. So this is how you try to find out true collapse load, that is 3 MP upon L. Fine. So this is one, these problems can be of this type. So if any problem of this type, you have to find out something like this. At the same time, they can ask what is the moment at B. What is the moment at B? They can ask that. Fine. What is the moment at B? They can ask that. How you are going to find that out? For that, consider free body diagrams of BE and EC. Fine. Considering free body diagrams of BE and EC, FBD of BE and FBD of EC. FBD of BE and FBD of free body diagram of BE and free body diagram of EC. So this will be, there is anti-clockwise moment. Here MB that you have to calculate. We don't know exactly what is the moment at B. I assume this as anti-clockwise. Okay. And here the moment developed is MP and load is W here. And here there is a clockwise moment of MP. Here also there is a clockwise moment of MP. Fine. And this is L. This is also L. So if it is, and W is what we got, W equals to 3 MP upon L. So what is the reaction here? Reaction R. What would be the reaction R here? If I take moment, this is C, this is E. Summation of moments about C equals to 0. Anti-clockwise minus R into L plus clockwise 2 MP equals to 0. R equals to 2 MP upon L. Fine. So R equals to 2 MP upon L. If R equals to 2 MP upon L, then reaction S would be equals to 3 MP minus 2 MP upon L, that equals to MP upon L. MP upon L, right? So here it is S. If you want moment at B, take summation of moments about B equals to 0, S into L clockwise, S multiplied with L clockwise, minus MP anti-clockwise, minus MB equals to 0. So MB would be equals to MP upon L into L. This is clockwise, this is anti-clockwise. Fine. And this is also anti-clockwise into L minus MP. So moment at B equals to 0. Moment at B equals to 0. In different problems you'll get different values. Anyway, this is how you'll try to find out the moments and reactions, everything, whatever you want. Just take the free body diagrams and try to find out the things. Okay, so this is how we'll generally in plastic analysis, these are the major points that we have revised, not major points, maximum amount of points we have revised. If you have done the problems, you would have seen even some more concepts over there. Okay, so the major concepts were revised over here. So with this, I'm closing this session. In the next session, we'll see you know, this connections. In connections, bolted connections, welded connections, and eccentric, different types of connections we'll see over there. Okay, fine. So next, quick revision, steel 4, session 4, quick revision, steel structures, session 4. Fine. So in this session, we'll see some of the special cases for plastic analysis. Fine. Special cases in plastic analysis. Special cases to find collapse loads. Special cases to find collapse loads. Collapse loads in plastic analysis. Special cases to find collapse load in plastic analysis. So in this, what we can see is generally sometimes a fixed beam with different capacities or cross-sectional areas is given to you. Let us say, see, this is just an example, don't think otherwise. Fine. The load is W, this is W, and I'll call this as, this is at a distance of L by 3. I'll take this as some MP, this as some 2 MP. A, B, C, D, and this distance as L upon 2. L by 2, this distance also as L by 2. This is L by 2. This is L upon 2. This is also L upon 2. These are some of the special cases. So here ds is how much? Ds equals to R minus S, number of reactions. What are the number of reactions here? 1, 2, 3, 4. There are 4 reactions. So number of reactions is 4. Number of equilibrium equations is 2. So ds equals to 4 minus 2, that equals to 2. Number of hinges required to be formed. Number of hinges required to convert this into mechanism. Number of hinges required equals to ds plus 1, that equals to 2 plus 1, that equals to 3. So 3 hinges has to be formed. And what are those locations? Thing is, it will form at the fixed supports, it will form at under the point load, it will form at the location where cross section changes or material changes. So it can form at A, C, D, B. In these 4 locations, 3 hinges can form. So you have to check all the criterias, all the different criterias. Fine. So here, let us say plastic hinges. At first, I'll take plastic hinges at A, C, B. Fine. Plastic hinges at A, C, B I am taking. If I take plastic hinges at A, C, B, how does the figure looks like? Loading will be somewhere here. This is L by 3. This is 2L by 3. This would be alpha and this is beta. Fine. Here it would be MP. Here also it would be MP. Here also it would be MP. But here at this location at B, it would be 2 MP because capacity of the member is 2 MP. Fine. So at B it would be 2 MP. So this is 2 MP. MP, MP, 2 MP, MP. Right? And this is beta. This one is alpha. And this is L by 3 times alpha. This is 2L by 3 times beta. So what I can write, L by 3 times alpha would be equals to 2L by 3 times beta. Beta equals to alpha upon 2. Beta equals to alpha upon 2. If I apply the principle of virtual work over here, applying principle of virtual work, applying principle of virtual work, applying principle of virtual work, external work done equals to internal work done, external work done equals to internal work done. Applying principle of virtual work, if external work done equals to internal work done, then what I can write over here is W times 2 alpha by W times L by 3 alpha external work done, W times L alpha by 3, that equals to internal work done. Internal work done MP times alpha plus beta and 2 MP times beta. So MP times alpha plus MP times alpha plus beta plus 2 MP times beta, right? So this would be equals to MP times 2 alpha plus 3 beta, that equals to W L by 3 times alpha, that is MP times 2 alpha plus 3 alpha by 2, that equals to 7 MP alpha upon 2, that equals to W L by 3 times alpha. So W equals to 21 MP upon 2L, that equals to 10.5 times MP upon L. This is one way of finding the load. This is only one way. This is only 10.5 MP upon L, right? 7 3 is 21 only. So this is 2 alpha plus 3 beta. Yeah. So our beta is alpha by 2, 3.5. 3.5 into 3, that is 10.5, right? So 10.5 MP upon L. This is collapse load if plastic hinges are forming at A, C and B. Next variation would be plastic hinges at A, D, B. You have to check that also. Plastic hinges at A, D, B. Fine. So plastic hinges at A, D, B. Plastic hinges at A, D and B. So if I try to write plastic hinges at A, D and B, this will be theta, this is also theta, and loading is somewhere here, W, this is W, this is theta, here anyway it is 2 MP and here it is MP. And always remember Always remember, if two members of different capacities are meeting, then failure will occur generally in weaker member. So in this problem over here, if you have to consider what is the capacity, MP and 2MP are meeting, you will be taking only MP, because two members of different capacities are meeting, then this would be theta. Here you will be taking MP, here you will not take 2MP, because failure will occur in the weaker member. So applying principle of virtual work, applying principle of virtual work, external work done equals to internal work done. External work done equals to internal work done. External work done equals to internal work done. Fine. So what you can write from here is W times this would be L by 3 times theta. This is L by 3 times theta, that equals to MP into theta plus 2MP theta. Fine. So W multiplied with L by 3 times theta, that equals to MP multiplied with theta plus MP multiplied with theta plus 2MP times theta. 2 plus 2, 4 plus 1, 5. That equals to 15 MP upon L. Fine. So W would be equals to 15 MP upon L. Collapse load for plastic hinges at ADB. Next, plastic hinges can form at ACD, right? Plastic hinges can also form at ACD. So next, plastic hinges at ACD. Plastic hinges at A comma C and D. Plastic hinges at ACD. What you can write from here is this is L by 3. Next one, let us say L upon 6. This is W. Fine. And this one is something like this. This is L by 3. This one is L by 6. Here it is MP. Let us say this is some alpha, this is some beta. Here it would be MP only. If two members of different capacities are meeting, failure will occur in the weaker member, right? So here it is MP. Here also it is MP. This is alpha. This one is beta, right? So applying principle of virtual work, what you can write? Applying principle of virtual work. Applying principle of virtual work. Applying principle of virtual work. External work done equals to internal work done. External work done equals to internal work done. External work done equals to internal work done. Applying principle of virtual work, external work done equals to internal work done. This is L by 3 times alpha, that equals to L by 6 times beta. So L by 3 times alpha equals to L upon 6 times beta. So beta equals to 2 times alpha. Beta equals to 2 times alpha. So if I substitute it over here, applying principle of virtual work, W times L by W into L by 3 times alpha, that equals to MP times alpha plus MP times alpha plus beta plus MP times beta. Fine. So this would be equals to 2 MP times alpha plus beta is 2 alpha, W multiplied with L by 3 times alpha. 2 3 6, 6 3 is 18. 18 MP upon L. Fine. This is the collapse load that you will get. Finally, what would be the true collapse load? True collapse load would be minimum of 18 MPa upon L, 15 MPa upon L, and 10.5 MPa upon L. So minimum of these three things is 10.5 MPa upon L. So true collapse load is true collapse load equals to 10.5 MPa upon L. So plastic hinges, correct failure mechanism is plastic hinges at A comma C and B is correct failure mechanism. Plastic hinges at A comma C and B is the correct failure mechanism. Fine. So this is how you'll try to find out plastic hinges at different, you have to find out collapse loads. This is one of the special case. Fine. This is just an example. Load can be anywhere. You have to check all the cases, and minimum of all the cases will be your collapse load. So check each and everything in the examination and accordingly try to answer it. This is one of the special case. Next special case would be propped cantilever beam with overhang. Propped cantilever beam with overhang subjected to UDL. So this is propped cantilever beam with overhang of length L by 3 subjected to UDL. In this case, what you will see, always remember, it's not complete structure failure. Part of structure failure is also considered as total collapse. That means here, if BC fails, if simply BC fails, that means a hinge is formed at B and simply BC fails, just this part fails, then we assume that total structure fails. Like in a whole structure, if a small part also fails, then we assume that total complete structure is failed, right? So a part of structure failure is also considered as total structure failure. That is the concept you will be seeing here, right? So part of structure failure is considered as total structure failure. Now anyway, what is ds here? Ds equals to R minus S. Number of reactions is 3, number of equilibrium equations is 2, right? Here there will be one reaction, 1, 2, 3, and ds equals to 3 minus 2, that equals to 1. Number of hinges required to be formed. Number of hinges required to convert into mechanism is ds plus 1, that is 1 plus 1. 2 hinges is required. So 2 hinges has to be formed. We don't know what is the location where first hinge will be formed here, second hinge we don't know where it will form. But anyway, first failure mechanism, failure of member BC, part of structure failure considered as total structure failure. Fine. So failure of member BC, if you consider failure of member BC alone, failure of member BC alone, that means plastic hinge at B, that is plastic hinge at B, that is plastic hinge at B. Generally, if it is hinge support, hinge will not form, but since it is continuous over that, since it is continuous over B, so hinge, there can be formation of hinge at B. Fine. So that is plastic hinge at B. Plastic hinge at B. Failure of member BC alone, that is plastic hinge at B. From this, what you can write is this is L by 3. Let us say this is some theta, and here MP will be there. This would be L by 3 times theta, and there is a loading over here. This will also be L by 3. This length is L by 3 and the loading is W kilonewton per meter. So plastic hinge is formed at B. We are not worried about AB, we are just saying if there is failure in member BC. So applying principle of virtual work, external work done equals to internal work done. External work done equals to internal work done. External work done equals to internal work done. So external work done is how much? Load multiplied with area under the load. W multiplied with half multiplied with 1 by 3 into L by 3 times theta equals to MP times theta. Right? So 9 to 18. W equals to W equals to 18 MP upon L square. W equals to 18 MP upon L square. Fine. So W equals to 18 MP upon L square. Simple. This is collapse load if there is failure in member BC alone. Next, if I consider total structure failure, that means 2 hinges has to be formed. And what are those locations? First hinge will form at A. Next hinge, it can form at anywhere in member AB, we don't know the location. So we will be using a free body diagram, FBD. Let us say it will form at a distance of x from here. If this is x, this would be L minus x. That is the location of D. Fine. Second hinge can form anywhere in the member AB. So let us say it is at D. So consider FBD of AD and FBD of DC separately. Considering FBD of AB, so if I have to write FBD of AD, so how exactly it would be? There is an UDL of W kilonewton per meter, and this is L minus X, this is MP, this will also be MP, and FBD of DB, this is MP, this is L by 3, this is X. Fine. Let us say this is AD and this one is D, B, C. If I take summation of moments about A equals to 0, what I'll get? MP, MP, minus MP, minus MP, plus W into L minus X whole square by 2 equals to 0. So MP would be equals to W multiplied with L minus X whole square upon 4. This is one thing. Next, take moments about B equals to 0. So from here it is MP minus W into X by 2 minus W X square by 2 and because of this one it would be clockwise, right? Plus W plus W into L by 3 into L by 6, that equals to 0. So MP equals to WX square by 2 minus W L square upon 18. Fine. So if I equate these two things, W into L minus X whole square by 4, W multiplied with L minus X whole square by 4 would be equals to wx square by 2 minus wl square upon 18 to 9. L minus x whole square would be equals to 2x square minus 2l square upon 9, or 18x square minus 9 times L minus x whole square minus 2l square. 9 into L square plus x square minus 2lx equals to 18x square minus 2l square. So 18x square minus x square 9x square plus 18lx minus 2 minus 10 minus 11 L square equals to 0. If you try to solve this, so x would be equals to 0.49 times L. Fine. Anyway, you have to remember this, but for your understanding I have solved it. Okay, so x would be equals to 0.49 times L. If this is 0.49 times L, this is 0.51 times L. So what would be this one? L multiplied with 0.51 L whole square upon 4. So W would be equals to 15.38 MP upon L square. Fine, 15.38 MP upon L square. If they ask what is the prop reaction, WB would be equals to 0.49 L plus WL upon 3. 0.49 WL plus 0.49 WL plus WL upon 3. So that is VB equals to 0.49 plus 0.333. 0.82 WL. This is the prop reaction. Fine. So from this you will get collapse load as 15.38 MP upon L square. From here you got 18.18 MP upon L square. So what would be the true collapse load? True collapse load equals to 15.38 MP upon L square. This is the true collapse load. .38 MP upon L square would be your true collapse load. 15.38 MP upon L square is your true collapse load. Fine. So try to remember these values and then you'll get your answer. 15.38 MP upon L square is your true collapse load, and this is how you have to consider. So the major thing I want you to see over here is, apart from FBDs, it is if a part of structure is failed, the total structure is assumed to be failed. If a part of structure fails, total structure is assumed to be failed. The same concept is generally applied in continuous beams. Same concept is generally applied in continuous beams. Let us take a continuous beam. This is a continuous beam of each, let us say L, 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 and capacity is same, MP, 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 MP. For everything capacity is MP only. L comma MP, L comma MP, L comma MP, L comma MP. So if beam is continuous over the support, then the supports are considered as fixed supports. That means if I call this as A, B, C, D, E. Fine. If I call this as B, C, D are considered as fixed supports. B, C, D are considered as fixed supports. A and E are considered as hinge supports because beam is not continuous over there, beam ends over there. So B, C, D are considered as fixed supports, and A and E will be considered only as hinge supports, right? Now if let us say there is UDL over here, UDL on top of it. Let us say there is a UDL on top of it. Now you don't find DS, you don't have to find DS, number of hinges required to be formed, everything is a bigger method. Now what we'll be doing is, part of structure failure comes over here. If this part alone fails, then we consider total structure is collapsed. So if this part alone fails, means it is like a propped cantilever beam, right? One end is fixed, other end is hinged. So for propped cantilever beam with UDL, this would be 11.656 MP upon L square. Collapse load for this. Collapse load. Part of structure failure. Here one end is fixed, other end is hinged. So part of structure failure, collapse load is 11.656 MP upon L square. And here if you see, this is both ends are fixed, this end is fixed, this end is fixed. Here also this is considered as both ends are fixed. Both ends are fixed. So for both the things, the collapse load will be same because both ends are fixed and subjected to UDL. So collapse load would be equals to 16 MP upon L square. 16 MP upon L square. L is same, MP is same here. If MP changes, then you have to calculate differently. Okay. So here MP is same, L is same, 16 MP upon L square for both the things. And finally, once again over here, it is propped cantilever beam because D is fixed, E is hinged. So the collapse load equals to, collapse load W equals to 11.656 MP upon L square. W equals to 11.656 MP upon L square, 16 MP upon L square, 11.656 MP upon L square. So these are the different concepts that you have to generally see. A part of structure failure, if a part of structure fails, then total structure is assumed to be failed. Then total structure is assumed to be failed. Fine. This is one thing. Next, instead of UDL, if there is point load, you just have to treat this as collapse, fixed, whatever that is. That means this you will be treating as propped cantilever beam. This you will be treating this as fixed beam. This also you will be treating it as fixed beam. So if point load is exactly at the center, then collapse load would be equals to 6 MP upon L. And here if point load is exactly at center, then collapse load equals to 8 MP upon L. If point load is exactly at the center, then collapse load equals to 6 MP upon L. Collapse load equals to 6 MP upon L. So minimum of these three things. So true collapse load equals to if they ask what is the true collapse load, minimum of all these three things, that is 6 MP upon L. That means at a load of 6 MP upon L, this two will fail. So we assume that total structure is failed. At a load of 11.656 MP upon L square, these two will fail. So we assume that total structure is failed. So what is the true collapse load here? True collapse load equals to 11.656 MP upon L square. This is true collapse load, 11.656 MP upon L square. That is true collapse load. Fine. So this is one of the points that we generally see, different cases. Fine. So if load is somewhere here, then just accordingly you remember the formula or you try to prove it. So if you want, just take the structure separately and do the problem. Take the structure separately and do the problem. Consider these two things as fixed support, or one end is fixed, other end is hinged. Okay. So these are the points. Next point would be, length of plastic hinge. Length of plastic hinge, or length of elastoplastic zone. Length of elastoplastic zone. Length of elastoplastic zone or length of plastic hinge. Fine. So how is that you are going to find out length of plastic hinge is, if I take a member, simply supported beam with point load at the center, simply supported beam with point load at the center, this is P, this is L by 2, this is also L upon 2. Simply supported with generally maximum bending moment diagram. This is BMD. So maximum bending moment will be at the center. So I said plastic hinge will be at the center, or maximum. So bending moment should be less than or equal to MP. That is your yield condition. Fine. So here it is MP. If here it is MP, somewhere here it would be MY. Somewhere here it would be MY. Here also it would be MY. Here it is MY. This one is also MY. I'll take this as theta, this also as theta. Fine. Somewhere here it would be MY. I'll call this distance as X, this distance as X. That means up to this point, this is in elastic zone. Elastic zone. Elastic zone means if you release the load, it comes back to its original shape. There will not be any residual strains. Up to this point, this will be in elastic zone. Elastic zone. And this area, this total area is called as elastoplastic zone. Elastoplastic zone. This total area is called as elastoplastic zone, and this length is called as length of plastic hinge or length of elastoplastic zone. This is LP, and this distance would be L by 2. This distance is L upon 2. Fine. And let us take this as some B, C, D, E, F. So triangles BEF and BCD are similar triangles, right? Triangles BEF and BCD are similar triangles. So from this, what you can write is tan theta. Tan theta equals to my upon x. Same tan theta equals to MP upon L by 2. Fine. So tan theta equals to my upon x, that equals to MP upon L by 2. So MP equals to L by 2 times my upon x. X would be equals to L by 2 times MP upon my. So that is L by 2 times shape factor. Fine. So x would be equals to L by 2 times shape factor. L by 2 times shape factor. Fine. And length of plastic hinge, LP equals to L minus 2x, that is L minus 2 times L by 2 times shape factor, L multiplied with 1 minus 1 upon shape factor. This is length of plastic hinge. Fine. Obviously LP equals to what? LP would be equals to total length is L minus x and x, 2x. So LP equals to L minus 2x. This is how you will try to find out length of plastic hinge or elastoplastic zone. So it actually depends on shape factor, that is cross section and type of loading. For simply supported beam with point load at the center, it is LP into L into 1 minus 1 by shape factor. If it is UDL, I'll be directly giving you the formula. So for a simply supported beam with UDL, W kilonewton per meter, UDL, of simply supported beam of length L, UDL, then LP is generally given as L multiplied with under root of 1 minus 1 upon SF. So length of plastic hinge depends on type of loading, cross sectional area or shape factor. Fine. Cross sectional area or shape of the area, cross sectional area or shape factor. Fine. Shape factor for different sections, it would be different. For rectangular, circular and different thing, it is different. So this is how you will try to find out length of plastic hinge. Fine. So in this session we have seen some special cases how to find out the collapse load, and we have to seen what is the length of elastoplastic zone or length of plastic hinge. In the next session we will see collapse load in the frames. Okay. So yeah, this is quick revision 3. Still also we are in plastic analysis only. I am taking some decent amount of time for plastic analysis because the probability of asking question from here is very much high. So I am taking some more amount of time. So please be patient over here. So quick revision, steel structures. This is session 3. Quick revision, steel structures, session 3. Okay. So just a minute, let me check whether mic is on or not. Mic is on. Fine. So we have seen how to find out collapse loads in simply supported beams. Now we will see collapse load in fixed beam with point load at center. Collapse load for fixed beam with point load, at center. Fine. So collapse load for fixed beam with point load at center, if you have to see this, if I take a fixed beam something like this and with point load at the center, let us say this is L upon 2, this is L upon 2, this is W. So what is ds? Degree of static indeterminacy, that equals to R minus S. Number of reactions 1, 2, 3, 4. Number of reactions is 4 and number of equilibrium equations is 2. So what are those equilibrium equations? Sigma Fy equals to 0 and sigma m equals to 0. Right? So ds would be equals to r minus s, 4 minus 2, that equals to 2, and number of hinges required to be formed. Number of hinges required to convert structure into mechanism, to convert structure into mechanism equals to ds plus 1, that is 2 plus 1, that equals to 3. Fine. So 3 hinges has to be formed over here. 3 hinges has to be formed. So what will be the locations? First one, hinges can form at fixed supports under the point loads at the location of maximum bending moment, and fine, here location of maximum bending moment under the point load, both the things will coincide. Fine. So here 3 hinges will form at 2 will be at fixed supports and 1 will be under the point load. Fine. So if I have to draw the collapse diagram, if I have to draw, beam will bend somewhere here. So 3 hinges will form 1, 2, 3. These are the locations of 3 hinges. Fine. This is the location of 3 hinges. It will bend in this format. Right? Okay. So if this is L upon 2, this is also L upon 2, and this will be theta. Here there will be MP. Here also, because plastic hinges are formed over there, you will be taking the internal force MP developed over there. Fine. Next, here it is MP. Here also it is MP. And this is L by 2 times L upon 2 times theta. This is also L upon 2 times theta. So if these are L upon 2 times theta, this is theta, this is also theta. Fine. And this is W. So applying principle of virtual work, what we can say over here is applying principle of virtual work, external work done equals to internal work done. So external work done equals to internal work done. So what we can write from here is W into L by 2 times theta. W external work done is W multiplied with L by 2 times theta equals to internal work done. Internal work done is MP into theta plus MP into theta plus MP into theta. Right? So MP multiplied with theta plus MP multiplied with theta plus theta plus MP multiplied with theta. This is 4. So W would be equals to 8 MP upon L. So collapse load for fixed beam with point load at the center, W equals to 8 MP upon L. Fine. Collapse load for fixed beam with point load at the center, W equals to 8 MP upon L. Fine. Next one. Fixed beam with UDL. Fixed beam with UDL. W kilonewton per meter. Fine. So fixed beam with UDL of length L. Fixed beam with UDL of length L. So what you can write over here is number of hinges that will be formed is 1, 2, 3. Fine, number of hinges that will be formed is 3 hinges. Same thing, because ds equals to how much? ds equals to r minus s, and number of reactions will be 4. Number of equilibrium equations is 2. ds equals to 4 minus 2, that equals to 2. And number of hinges required to be formed. Number of hinges required to convert this into mechanism. Number of hinges required to convert this into mechanism is ds plus 1, that is 2 plus 1, that equals to 3. 3 hinges are to be formed. First 2 hinges will be formed at fixed ends. Next, third hinge will be formed at the center, because this is the location of maximum bending moment. Or actually first hinges will be formed at the ends, right, at a load of WL square by 12. Fine. Generally, what is the fixed end moments? If it is subjected to this WL square upon 12. So first yielding will occur over here. Finally, bending will occur when, or failure will occur when third hinge is formed at the center, right? You must be knowing this from here. So here what we can say over here is, this is how it will try to bend. This is L by 2. This is also L upon 2. This is theta. This is theta. Fine. And this is MP. This is also MP. This is theta. This is also theta. Fine. And this one is MP. This is also MP. Okay. MP, MP. Fine. If you apply the principle of virtual work, applying principle of virtual work, applying principle of virtual work, principle of virtual work, what we can write? External work done equals to external work done equals to internal work done. External work done equals to internal work done. External work done equals to internal work done. So W multiplied with, what is this area? Area would be half L into L theta. W multiplied with half multiplied with L by 2 times theta into L. Internal work done. Internal work done is MP, 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 MP. Fine. So what we can write over here is MP into theta plus MP multiplied with theta plus theta plus MP multiplied with theta, right? So W would be equals to 16 MP upon L square. Collapse load W equals to 16 MP upon L square. Collapse load W equals to 16 MP upon L square. Fine. This is collapse load for fixed beam with UDL. Fine. So first, if they ask what is the how the loads will be formed, generally if you see how the plastic hinges will form, first plastic hinges will form at the fixed ends and third plastic hinge will form at C. So plastic hinges first, two plastic hinges will form at A and B simultaneously. Followed by plastic hinge at C. At C. Fine. So generally you know it will form at WL square upon 12, or at a load of W equals to 12 MP upon L square. First plastic hinge will form at the ends. Generally negative moment is more compared to that of positive moment. So first plastic hinges will form at ends, followed by next plastic hinge. That means you'll keep on applying the load. At a load of 12 MP by L square, the plastic hinges will generally, if you see, I'll also write yielding 12 My upon L square. At 12 my upon L square, plastic hinges will form at A and B. Next, if you further increase the load up to 16 MP upon L square, 16 MP upon L square, final plastic hinge will form at C and total collapse you will be seeing over there. So if they ask yield load, this is yield load. This is yield load. If they ask yield load, this is your yield load. At this load yielding occurs. Yielding means plastic hinges will develop at A and B simultaneously, and if you further increase the load up to 16 MP upon L square, then this is the collapse load. Collapse will be occurring at C. This is collapse load. I am going at faster rate because this is quick revision. We are revising it. Fine, we are not wasting our time over here. So this is how you will be seeing that. Next, fixed beam with point load anywhere. Fixed beam with point load. Fixed beam with point load anywhere on the beam. Fixed beam with point load anywhere on the beam. Fixed beam with point load anywhere on the beam. L upon 2, L upon 2. Fine, here also I am saying point load anywhere, right? Not exactly at the center. Fixed beam with point load anywhere on the beam. Let us say this is A, this is B, this is W. Fine. So this is alpha, this is beta. ds equals to R minus S. Number of reactions is 4, number of equilibrium equations is 2. ds equals to 4 minus 2, that equals to 2. Number of hinges required to be formed. Number of hinges required to be formed. Number of hinges required to be formed is ds plus 1, that is 2 plus 1, that equals to 3. And what are the locations of 3 hinges? These are the locations of at fixed supports and under the load. Fine. So this is A alpha, this would be B beta, MP, 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 MP. Fine. So if you apply the principle of virtual work, applying principle of virtual work, applying principle of virtual work, applying principle of virtual work, external work done equals to internal work done, external work done equals to internal work done, external work done equals to internal work done. So that external work done would be equals to W times A alpha, that would be equals to MP times alpha plus MP times alpha plus beta plus MP times beta. Fine. And A alpha equals to B beta. From this, beta would be equals to A alpha upon B. Right. If I substitute it over here, W multiplied with A alpha, that equals to MP times 2 alpha plus 2 beta, that is 2 MP times alpha plus beta equals to A alpha by B, right? So that would be equals to 2 MP times B plus A alpha upon AB equals to W times alpha. W would be A plus B equals to L. So 2 MP L upon AB. that is the collapse load with for a fixed beam with point load anywhere. Collapse load for fixed beam with point load anywhere. Sir, why you are giving me all these proofs so that I'm doing it faster rate, so that you'll get huge amount of practice with this, because practice is important over here. You should know how to apply work done, apply the principle of virtual work, very much important. If you know how to apply this, you can solve any problem, whether it is beams, frames, any problem, you can easily solve that. You have to remember this. If it is a simple case, then go with it. If it is a complicated case, then apply principle of virtual work. Fine. So this is for fixed beam. In fixed beam with point load at center, collapse load is 8 MPa upon L. Fixed beam with UDL, collapse load is 16 MPa upon L square, and fixed beam with point load anywhere 2 MPa upon A. This is fixed beam. Next, propped cantilever beam. Propped cantilever beam with point load at center. Propped cantilever beam with point load. Propped cantilever beam with point load at center. So what you can write for this? If I take this as W, fine. Propped cantilever beam with point load at center. What is ds for this? Ds is R minus S. Number of reactions 1, 2, 3. Number of reactions is 3. Number of equilibrium equations is 2. So ds equals to 3 minus 2, that equals to 1. Number of hinges required to be formed. Number of hinges required to be formed to convert into mechanism equals to ds plus 1, that is 1 plus 1, that equals to 2. 2 hinges has to be formed. 2 hinges has to be formed. What are the locations of 2 hinges? First one is over here at the fixed support. Next one will be generally under the load. Fine, that will be the location of maximum bending moment, so it will form at the hinge. So these are the locations of 2 hinges. Fine. If this is the locations of 2 hinges, then what you can write from here is, if you try to draw the collapse diagram, if this is theta, this is L by 2, this is also L by 2, this is theta, this is L by 2 times theta, this is also L by 2 times theta, load is W, here it is MP, here also it is MP, here also it is MP, and this is theta, this one is also theta. Fine. So applying principle of virtual work, what we can say is, let me check whether mic is on or not. Constantly I have to check this. Yeah. Fine. So applying principle of virtual work, applying principle of virtual work, applying principle of virtual work, external work done equals to internal work done. External work done equals to internal work done. External work done equals to internal work done. So what I can write over here is W times L by 2 into theta would be equals to MP times theta plus MP times theta plus theta. Fine. So W would be equals to 6 MP upon L. So collapse load for propped cantilever beam with point load at center is 6 MP upon L. Collapse load for propped cantilever beam with point load at center is 6 MP upon L. Fine. MP times theta. This is MP times theta here and MP times theta plus theta. Fine. So collapse load equals to 6 MP upon L. This is propped cantilever beam with point load at center. Next, propped cantilever beam with UDL. Propped cantilever beam with UDL. Propped cantilever beam. Propped cantilever beam with UDL. Propped cantilever beam with UDL. W kilonewton per meter. Here one of the important thing over here is ds equals to same thing, ds equals to r minus s, r equals to 3, s equals to 2. So ds equals to 3 minus 2, that equals to 1. And number of hinges required to be formed, number of hinges required equals to ds plus 1, that is 1 plus 1, that equals to 2. 2 hinges is to be formed. What are the locations of those 2 hinges? This is location of one hinge, and what is the location of another hinge? We don't know here. This will not be exactly at the center. No, you have to draw the bending moment diagram, and finally if you see, it will not be at the center. Fine. It will be at certain distance from here. We don't know the exact distance. We have to find out that distance. We don't know that distance. Let us say the distance from here would be some x, and this would be L minus x. L minus x. Location of second plastic hinge, you don't know, right? And let us say this is at a distance of x, this is at a distance, that means from fixed support it is at a distance of L minus x. Now what you will be doing over here is, you will be using free body diagrams. You will be using the concept of FBD. To explain you the concept of FBD, I am doing it over here. Fine. So if I take FBD of AC and CB separately, FBD of AC, free body diagram of AC. So free body diagram of AC would be something like this. Here it is anti-clockwise, here also it is anti-clockwise, and then loading would be W kilonewton per meter. This is W kilonewton per meter, and this one is MP, this is also MP. And here also it is clockwise moment MP. There will be a support over here. Fine. So this is how you will be seeing it. Fine. If I take let us say I'll take summation of moments about A or C equals to 0. You can take anything. If I take summation of moments about A equals to 0, MP, MP, anti-clockwise, this is L minus X. So minus MP plus W into L minus X multiplied with L minus X upon 2, that equals to 0. So this would be W L minus X whole square would be equals to 4 MP. 4 MP, or MP equals to W L minus X whole square upon 4. W L minus X whole square upon 4. This is one point. Next, this is X, this is C, this is B. If I take summation of moments about B equals to 0, find MP clockwise minus W X into X by 2 equals to 0. So MP equals to W X square upon 2. So from here you will get, this is FBD of CB, free body diagram of FBD of CB, and this is FBD of AC. MP equals to W L minus X whole square upon 4, MP equals to W X square upon 2. So from this what you can write, MP equals to W X square upon 2 would be equals to W L minus X whole square upon 4. So 2x square would be equals to L minus x whole square. So L minus x would be equals to root 2x. L equals to root 2 plus 1 times x. X would be equals to L upon root 2 plus 1. X would be equals to L upon root 2 plus 1. What is this 1 upon root 2 plus 1? Generally, I think you'll get 0.414. 0.414 L, right? The value you have to remember. Fine. Generally, I'll have some doubts, so I'll cross check it. So x equals to 0.414 L, and if this is 0.414, this would be 0.586 L. So from prop reaction, second hinge will form at a distance of 0.414 L. It will not form at center. Okay, it will be forming at a distance of 0.414 L, and MP if you substitute it, that would be W into 0.414 L whole square upon 2. So W would be equals to generally 11.656 MP upon L square. So collapse load with propped cantilever beam subjected to UDL. Collapse load for propped cantilever beam subjected to UDL, W equals to 11.656 MP upon L square. And if they ask what is the prop reaction, VB equals to a summation of forces in y direction equals to 0. If I take here, if I take summation of forces in y direction equals to 0, VB equals to W into X. W multiplied with X, that is 0.414 WL. This is VB. This is prop reaction. So for a propped cantilever beam subjected to UDL, collapse load W equals to 11.656 MP upon L square, and prop reaction VB from plastic analysis. This is not elastic analysis. From plastic analysis, VB equals to 0.414 WL. This is from plastic analysis, not from elastic analysis. In elastic analysis, if you have to use method of superimposition. That means because of this load, what is the deflection over here, and because of reaction, what will be deflection over here. Sum of the deflections equals to 0. If you take that, you will get prop reaction from elastic analysis. I'll show it to you over here. Fine. Just for your understanding, I am showing it here. Okay. Prop reaction from elastic analysis if they are asking. Because of the loading, it will try to bend something like this. Fine. So delta at B would be equals to W L power 4 upon 8 EI, right? W L power 4 upon 8 EI. If it is W and this is L, W L power 4 upon 8 EI. And because of prop reaction, what would be the delta B? Prop reaction would be something like this. Delta B. If let us say VB is the prop reaction, if this is L, this is VB L cube upon 3 EI. VB L cube upon 3 EI. And total deflection would be equals to 0, right? Final deflection, because here it would be hinged. Hinged means in this direction deflection equals to 0. So final delta B equals to 0. If I use that, delta B equals to 0, then what I'll write, VB into L cube upon 3EI minus WL power 4 upon 8 EI. So VB prop reaction would be equals to 3 upon 8 WL. This is prop reaction from elastic analysis. Prop reaction from elastic analysis. And prop reaction from plastic analysis, VB equals to 3 upon 8 WL. prop reaction from plastic analysis, you got it as prop reaction from plastic analysis. Prop reaction from plastic analysis, you will get it as something like VB equals to 0.414 WL. So read the question properly, whether they are asking elastic analysis or plastic analysis, and accordingly try to find out. Fine, there was a problem in the gate, but for point load he has given. For point load also you can calculate that, right? Suppose if they are saying with for point load at the center, prop reaction from elastic analysis and prop reaction from plastic analysis, if they are asking, let us say. For point load at the center, you get the collapse load as something 6 MP upon L. Fine, anyway, first, what is the prop reaction from the elastic analysis? If you have to see that, if I take this as some W, if you use method of superimposition, this is L by 2, this is also L by 2. Because of load at C, what is the deflection at B? All these things are your strength of materials concepts, right? So prop reaction because of load at C, it will try to bend something like this. This is C, this is W, this is L upon 2, this is also L upon 2. Delta C, this would be theta C. So this would be L by 2 times theta C, and this is delta C. This total is delta B, right? So because of point load, what is delta B? That is equals to generally PL cube upon AE WL by 2 whole cube upon 3EI plus WL by 2 whole cube upon 3EI plus theta. Theta would be WL square upon 2EI plus L by 2 times theta C, that is W L by 2 whole square upon 2EI. So what I can write over here is W L by L cube upon 8EI, if I take common, 1 by 3 plus 1 by 2, that is 5 WL cube upon 648 EI. This is delta B because of the load. And due to prop reaction, what would be delta B? If you are applying prop reaction, it tries to bend something like this. This is delta B. Let us say this is VB. So delta B would be equals to, if this is L, this is equals to VB L cube upon 3EI. VB L cube upon 3EI. Fine. So total delta B, if I take equals to 0, then what I will get? VB multiplied with L cube upon 3EI, that equals to 5 upon 48 WL cube upon EI. So VB equals to 5 upon 16 W. This is prop reaction from elastic analysis. Prop reaction from elastic analysis. Prop reaction from elastic analysis. Okay. Now, prop reaction from plastic analysis, how you will see? For that, you just have to consider prop reaction from plastic analysis. If they ask what is the prop reaction from plastic analysis, the idea should be very much simple. This is W, this is L by 2, this is also L by 2. So here one hinge, plastic hinge will be formed. here another plastic hinge will be formed. Okay, so if I consider FB is A, C, if I consider FBD anti-clockwise, and here also this is clockwise, and this one is reaction over here, and a total load of W is being applied here, right? So if it is W and this is MP, this is also MP, this is also MP, L by 2, this is also L upon 2. Fine. And let us say there will be a reaction over here. Fine. I'll call this as some reaction R. If I take summation of moments about A equals to 0, R into L by 2, that is clockwise, R multiplied with L by 2 clockwise equals to MP plus MP, that is 2 MP. R equals to 4 MP upon L. R equals to 4 MP upon L. W is how much generally? 6 MP upon L. Out of this, R equals to 4 MP upon L. If R equals to 4 MP upon L, then what would be the reaction over here? I'll call this as some S, that would be 2 MP upon L. 2 MP upon L. And this is, let us say, prop reaction VB. For this beam, if I take summation of forces in y direction equals to 0, only for this part, VB equals to S, that equals to 2 MP upon L, that equals to W upon 3. This is prop reaction from plastic analysis. Prop reaction from plastic analysis is W by 3. So VB equals to W upon 3. Prop reaction from plastic analysis. Prop reaction from plastic analysis. Okay, this is how you'll try to find out prop reactions by using free body diagrams. Okay, just that means, see, this is revision. That means one class is enough where you have already read all these things, and I am trying to brush up. Okay, this is how we have done at that point of time. This is how we have read at that point of time. So just showing this, that is the reason I am going at faster rate. Okay, so this is prop reaction from plastic analysis, prop reaction from elastic analysis. These are another 2 points. Okay, so in propped cantilever beams with point load at the center, collapse load is 6 MP upon L. For propped cantilever beam with UDL, collapse load is 16.656 MP upon L square, and the prop will, second hinge will be forming at a location of 0.414 L from the prop reaction. Okay, next point is propped cantilever beam with point load anywhere on the beam. Propped cantilever beam with point load anywhere on the beam. With point load anywhere on the beam. Propped cantilever beam with point load anywhere on the beam. For this, what you can write over here is anywhere. Okay, let us say this is A, this is B. Fine, and this whole length is L. A number of hinges required to be formed. Number of hinges required to be formed, anyway ds equals to 1 here. Number of hinges required is number of hinges required to be formed. Number of hinges required to be formed. Number of hinges required to be formed equals to 1 plus 1, that equals to 2. 2 hinges has to be formed, and what are the locations? The possible locations will be here and here. This is alpha, this one is beta, and this is MP. If I take, this will also be MP, and this is alpha, this one is beta. What I can write is A alpha equals to B beta, A alpha equals to B beta, beta equals to A alpha upon B, beta equals to A alpha upon B. Fine. So here there will be another plastic hinge. So applying principle of virtual work, what we can write is applying principle of virtual work, applying principle of virtual work, external work done equals to internal work done, external work done equals to internal work done, external work done equals to internal work done. So external work done would be equals to how much? If I take this as W, W times A alpha equals to MP times alpha plus beta, that's it, right? So W times A alpha equals to MP times alpha plus MP times alpha plus beta, right? So W times A alpha equals to MP times 2 alpha plus beta, beta is A alpha by B, so that is equals to MP times 2B plus A upon AB equals to W. So W would be equals to MP times L plus B upon AB. This is the collapse load for point load anywhere on the beam of, on a propped cantilever beam. This is the collapse load. Fine. So you have to find out something like this. You can easily find out by using the theory, by using this concept, you can easily find out. And the final things that you have to remember over here is, for a simply supported beam with point load at center, for a simply supported beam with point load at center, and for a propped cantilever beam with point load at center, and for a fixed beam with point load at center. For a simply supported beam with point load at center, for propped cantilever beam of length L with point load at center, for fixed beam of length L with point load at center. Fine. So collapse load equals to, for this one it is 4 MP upon L collapse load, and collapse load for this one equals to 6 MP upon L, and collapse load for this one equals to 8 MP upon L. Fine. So it will be in the increasing order. Okay. Next for a simply supported beam with UDL, for a simply supported beam with UDL, for a simply supported beam with UDL, collapse load would be equals to 8 MP upon L square, collapse load would be equals to 8 MP upon L square, and collapse load for propped cantilever beam with UDL of length L, for propped cantilever beam of length L, and for fixed beam with of length L with UDL, collapse load for this one equals to 11.656 MP upon L square, and collapse load for this one would be equals to 16 MP upon L square. Fine. So these are the points that you have to remember. You don't have a choice. Fine. Okay. So in this session, I have shown you how to find out the collapse load for fixed beam and for propped cantilever beams, and there are some special cases that we'll discuss in the next session. Okay. This is quick revision of steel structures, second lecture. Fine. So quick revision of steel structures. Quick revision steel, your lecture 2. Fine. So in this, what we'll be seeing is, in previous class we have seen what is plastic moment assumptions, plastic moment capacity, shape factor, load factor, relationship between moment and curvature. Now we will be seeing something called collapse loads. Fine. Collapse load, the name itself says collapse load. Collapse load, the load at which, collapse load is the load at which material collapses, the load at which structure fails, the load at which structure fails, or structure is converted into mechanism. Structure is converted into mechanism. That means there will be rigid mechanism, means indirectly this is the position where member behaves like a rigid body motion. There will not be any elastic deformations. Fine. Mechanism is the stage. Mechanism is the stage where structure behaves in rigid body movement, where structure behaves in rigid body motion, without any elastic deformations, without any elastic deformations. Fine. So anyway, that the collapse load is the load at which structure fails or structure is converted into mechanism. Suppose if I take a simple structure, if you keep on applying the loading, let us say simply supported beam. I will take a simply supported beam. Let us say you are applying the load something like this. Fine. W is your load. Initially, because of the loading, there will be this type of bending, and then with increase in the loading, there will be bending, and there comes a point where there will be complete failure of the structure. This is at plastic stage. Or collapse condition. At plastic stage or collapse condition. Fine. At plastic stage or collapse condition, this is the variation of the bending moment, variation of the beam. That means beam fails. That means indirectly a plastic hinge is formed. So if a plastic in the problem, if they are saying a plastic hinge is formed, that means indirectly collapse has occurred. A plastic hinge is formed and collapse has occurred. Fine. So this is at plastic stage, or this is where mechanism happens. As I said, rigid body motion. That means if you apply the load, this whole thing will rotate. Whole body will move, or whole thing will rotate. There will not be any elastic deformations over here. You won't see anything of that. So whole body will rotate. This is mechanism or rigid body motion. Fine. So this is how you will see the collapse load. Fine. So where whole body is converted into the mechanism. Generally, there are three conditions that should be satisfied to find out the collapse load. First one is equilibrium condition. Idea is to find out the collapse load. For the three conditions is what we'll be generally seeing. Okay, so that is sigma fx equals to 0 and sigma fy equals to 0. And summation of moments equals to 0. If a body is in equilibrium, then all these three conditions must be satisfied. Next one is mechanism condition. mechanism condition. For sufficient number of plastic hinges, what exactly is mechanism condition is sufficient number of plastic hinges, sufficient number of plastic hinges, sufficient number of plastic hinges, sufficient number of plastic hinges is to be formed, sufficient number of plastic hinges is to be formed to convert a stable structure, to convert a stable structure into mechanism, to convert a stable structure into mechanism, sufficient number of plastic hinges must be formed. Sufficient number of plastic hinges must be or is to be formed to convert a stable structure into mechanism. Fine. To convert a stable structure into mechanism. Generally, what are the number of plastic hinges required to be formed? Suppose stable, we are trying to convert stable structure into mechanism means let us say this is a simply supported beam with loading at the center. Let us say this is W. Fine. Number of reactions, you will be considering only vertical reactions. So let us say there is one reaction here and there is another reaction here. Degree of static indeterminacy. Degree of static indeterminacy is generally given as R minus S. R is number of reactions here, number of reactions is 2 and number of S is number of equilibrium equations, right? R equals to number of reactions and S equals to number of equilibrium equations. Number of equilibrium, S equals to number of equilibrium equations. Fine. So that is sigma fx equals to 0, comma, what are those equilibrium equations here? Generally equilibrium equations are 3, but for vertical loading equilibrium equations will be 2, that is sigma fy equals to 0 and summation of moments equals to 0. Summation of moments equals to 0. See, for different types of loadings, here it is, we are not considered the global loading. If it is global loading, then you will be using 3 equations of equilibrium, but here you are considering only vertical loading. For vertical loading, these are the equilibrium equations that you will use. Sigma fx equals to 0, we don't use that. So ds would be equals to R minus S. Here number of reactions is 2, number of equilibrium equations is 2. So ds equals to 0. If ds equals to 0, number of plastic hinges, now ds equals to 0. Okay, that means it is stable and determinate structure. You have to convert this into unstable structure. If you have to convert this into unstable structure, then one more plastic hinge, one more than ds. That means one plastic hinge is enough to make this structure unstable, right? So let us say this is the where plastic hinges form. This is the location where plastic hinges are formed. So if this is the location of plastic hinge, it will rotate something like this. It will try to bend something like this, right? So if a plastic hinge is formed over here, that means it fails. Structure is failed. Okay, so structure is failed. If a plastic hinge is formed over here, structure is failed. Okay, so if structure is failed, number of, that is what I am saying, ds equals to 0 over here. So one plastic hinge is enough to convert this whole structure into unstable structure or mechanism. So number of hinges required, generally how you can see over here is number of hinges required to convert number of hinges required to convert a structure into mechanism, number of hinges required to convert a structure into mechanism equals to ds plus 1, that is 0 plus 1, that equals to 1. Number of hinges required to convert a structure into mechanism is 1. ds plus 1, that is 1. So always Number of plastic hinges required to convert a structure into mechanism is generally given as ds plus 1. So here 1 is enough. If it is fixed beam, we will be requiring 3. If it is propped cantilever beam, we will be requiring 2. So that is the idea. So sufficient number of plastic hinges is to be there to convert a structure into mechanism. That is your mechanism condition. Next one is yield condition. Yield condition. Fine. So bending moment at any section, bending moment at any section, bending moment at any section, bending moment at any section should be less than, bending moment at any section should be less than plastic moment capacity. Plastic moment capacity. It should not be more than this. That is yield condition. Bending moment at any section should be less than plastic moment capacity. So what exactly it means is, if you are taking a beam and you are applying the load, something like this, if you are taking a beam and you are applying the load, something like this, then what exactly happens is, this is the bending moment diagram, BMD, right? This is bending moment diagram. So bending moment at any location, that means here also if I take the maximum bending moment should be less than or equal to MP. It should not be more than MP. MP is the plastic moment capacity, that is property of the material, right? So it depends, for a given area, MP equals to Fy multiplied with Zp, or Fy multiplied with A by 2 multiplied with Y1 plus Y2. So Fy is property of material, area is also for a given area, MP remains constant. So Y1 and Y2 also we know. So MP equals to Fy multiplied with Zp, that is what we try to see generally, right? So now number of plastic hinges required to be formed is 1, and okay, these are the different conditions. And if equilibrium and mechanism now there are two types of theorems, kinetic theorem or kinematic theorem and static theorem. Kinematic method, to find out the collapse loads, there are two methods. First one is kinematic method. Kinematic method. Kinematic method. Upper bound theorem. Kinematic method, upper bound theorem. Fine. So equilibrium and mechanism condition is satisfied. Equilibrium and mechanism condition is satisfied. Equilibrium and mechanism conditions is satisfied. Collapse load is more than or equal to true collapse load. Collapse load is more than or equal to true collapse load. Fine. So collapse load is more than or equal to true collapse load. This is kinematic method. The collapse load obtained by kinematic method. This is upper bound theorem, where equilibrium condition and mechanism condition is satisfied. Only these two conditions are satisfied. Equilibrium and mechanism condition is satisfied. Equilibrium and mechanism condition is satisfied, and if equilibrium and yield condition is satisfied, that is also called as static method. In static method, lower bound theorem, static method, lower bound theorem, static method, lower bound theorem, static method, lower bound theorem. So what you can write over here is equilibrium and yield condition, equilibrium and yield condition is satisfied. Equilibrium and yield condition is satisfied. Load obtained, collapse load obtained is less than or equal to true collapse load. This is collapse load obtained from this method. Collapse load obtained is less than or equal to true collapse load. Collapse load obtained by this method. Fine, that is why this is called as lower bound theorem, where collapse load that obtained is less than or equal to true collapse load, and collapse load obtained over here is more than or equal to true collapse load. This is in kinematic method upper bound theorem. This is static method, that is lower bound theorem. Fine, kinematic method and static method. Equilibrium condition, mechanism condition is satisfied here. Equilibrium condition and yield condition is satisfied here. If all the three conditions are satisfied, then we obtain a unique collapse load, that is called as true collapse load. If all the three conditions are satisfied, then we obtain a unique collapse load, then we obtain a unique load which is called as true collapse load, then we obtain a unique load which is called as true collapse load, that is generally given as PU. Fine. So equilibrium condition, mechanism condition and yield condition is satisfied over here. Equilibrium condition, mechanism condition, and finally yield condition. If all these three conditions are satisfied, then we obtain a unique collapse load, that is called as true collapse load. Fine. So that is given as PU. Fine. Now we can't use all these type of methods, so what we'll be using is principle of virtual work. So work done by all the loads and internal forces, combined work done by all the forces, loads and internal forces is taken as 0. That is the principle of virtual work. So throughout the analysis, these are some of the ideas, some theory behind this in collapse load, but throughout the analysis we will be using principle of virtual work to find out the collapse load. Fine. So what exactly is principle of virtual work? If I have to write principle of virtual work, work done by summation of work done by all the forces, work done by all the loads, work done by all the external loads, and internal forces, summation of work done by all the external loads and internal forces is taken as 0. So work done by external loads, work done by external loads plus work done by internal forces equals to 0. Internal force means majorly that is moment. Work done by internal forces, if you remember, is in equilibrium, work done by all the forces, work done by the loads and forces, summation of work done by loads and forces equals to 0. So work done by all the external loads and internal forces is equals to 0. Fine. So you have to remember this point. This is principle of virtual work. How exactly we are going to use this, we'll see that. I'll try to explain it through an example. Let us take a simply supported beam. simply supported beam with point load at center, with point load at center. Before that we have to see what are the locations of collapse loads. I'll discuss that also. Fine. Let us take a simply supported beam with point load at the center. Point load exactly at center. If I take this as W, this would be L by 2, this will be L by 2. What is ds here? Degree of static indeterminacy. Generally it is given as R minus S, 2 minus 2, ds equals to 0, and number of plastic hinges required to be formed, number of plastic hinges required to be formed, number of plastic hinges required to be formed equals to ds plus 1. Number of plastic hinges required to be formed is equals to ds plus 1. So to convert this into mechanism, that is 0 plus 1, that equals to 1. So one plastic hinge is to be formed. And what is the location of plastic hinge? Fine. So generally if you see the location of the plastic hinges, this point is also important. Location of plastic hinges, location of plastic hinges, location of plastic hinges. Generally at the location of maximum bending moment, plastic hinges can be formed at the location of maximum bending moment, at the location of maximum bending moment, at the location of maximum bending moment. So first point is at the location of maximum bending moment. Location of plastic hinges, first one is at the location of maximum bending moment. Next, under the point loads, it can form under the point loads, under the point load. Next, at fixed supports, at fixed supports, it can form at fixed supports, it can form at fixed supports. Cross section where material changes, or location where material changes. Okay, location where material changes, location where material changes, and location where cross section changes, and location where cross section changes, location where material changes and location where cross section changes. So at the location of maximum bending moment, under the point load, at fixed supports, location where material changes and location where cross section changes. Location where material changes means that can also act as the weak point. Fine, that can also act as the weak point. So that means up to some point it can be steel, other point it can be aluminum. So this also can be a location of plastic hinge. Plastic hinge can also form over here. Plastic hinge can form under the load. Plastic hinge can form under the load, and it can form at the fixed supports. It can form here, it can form here, it can form here, and at the location of maximum bending moment it can form over there also. So you have to check all the criterias, and finally you have to design where you will get the minimum collapse load, for which load, for which condition you are getting minimum collapse load, you will be considering that as your true collapse load. Fine. So if I take a simply supported beam, number of plastic hinges required to be formed as 1, and what is the possible location? This is the location where This is the, at the center there is maximum bending moment, at the same time this is exactly under the load. So plastic hinge will form exactly over here. Fine. So if plastic hinge is formed here, then if you have to draw the collapse diagram, fine. So there is an anti-clockwise moment over here, there will be anti-clockwise, there will be clockwise, there will also be a clockwise moment over here. Fine. If I take this as theta, this would be L by 2 times theta, this is also L upon 2 times theta. I'll take this as some theta, and this is equals to MP, this is also equals to MP. Fine. That is what I am saying. So here this is a virtual thing, it will not exactly bend like this. At the collapse condition, it tries to rotate like this. This is at collapse condition. Fine. And internal forces that is developed is at collapse condition. So work done by external load multiplied with distance in the direction of load applied, and work done by internal forces. So here this is the work done by the internal forces. It tries to rotate it like this, and internal force tries to resist like this. Anyway, these are hinges, moments will not develop at the ends. Moment, only one plastic hinge is formed, so moment will be developed something like this. If it is MP, this is theta, and MP and theta are in opposite direction, so work done by the internal forces is negative. W and L by 2 times theta, both are in same direction, whereas MP is anti-clockwise here, theta is clockwise. MP is clockwise, theta is anti-clockwise here. Fine. So applying principle of virtual work, applying principle of virtual work, external work done plus internal work done external work done plus internal work done, or work done by internal forces equals to 0. Sorry, not 1, it is 0. Fine. Or indirectly what you can write down is external work done equals to internal work done, external work done equals to internal work done, or work done by external forces equals to internal work done. So W multiplied with work done by external force, W multiplied with L by 2 times theta equals to internal work done equals to MP multiplied with theta plus theta. This is MP, here it is MP into theta, right? So MP multiplied with theta times theta, so MP multiplied with theta plus theta, W equals to 4 MP upon L. This is how you'll try to find out the collapse load. Collapse load for an SSB with point load at center. Collapse load for a simply supported beam with point load at the center. You have to remember this value. If you remember, you have to know the concept to solve different types of questions. And if you remember this value, some match the following questions will be solved easily. A simply supported beam with point load at the center, collapse load is 4 MP upon L. So always remember, apply principle of virtual work, external work done equals to internal work done, then collapse load is something like this. So similarly, in similar lines, if you go for simply supported beam with UDL, W kilonewton per meter, W kilonewton per meter, SSB with UDL, and if I take this as some length L. Anyway, ds will not change. This is a stable structure. ds equals to 0. Number of plastic hinges required to be formed, number of plastic hinges required, number of plastic hinges required to convert it into mechanism, to convert the structure, into mechanism, number of plastic hinges required to convert the structure into mechanism equals to ds plus 1, that equals to 0 plus 1, that equals to 1. One plastic hinge is required to convert the whole structure into mechanism, so that plastic hinge is generally formed at the center, because bending moment will be maximum at the center, so plastic hinge will form over here. This is simply supported beam with UDL, simply supported beam with UDL, so plastic hinge will be formed at the center, right? So it will try to rotate something like this, fine. So if this is L, this would be L by 2, this is also L by 2, this is theta, this will also be theta, this would be L by 2 times theta, this is also L upon 2 times theta, and here it would be MP, this one is also moment is MP, this is theta, this is also theta, fine. So if you apply the principle of virtual work over here, applying principle of virtual work, 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 external work done equals to internal work done, external work done equals to internal work done, external work done equals to internal work done, or work done by external forces equals to work done by internal forces. So what you can write over here is here it is UDL, so load multiplied with area of this whole thing you have to consider, you will not be considering a single direction. So W multiplied with area of this whole thing, that is half into this area of triangle, half into L by 2 theta into L, right? So work done by external forces is, external work done would be equals to W multiplied with half L by half into L by 2 times theta multiplied with L, that is work done by internal forces is MP times theta plus theta. So W would be equals to 8 MP upon L square. This is the collapse load, collapse load with UDL, collapse load of SSB with UDL, collapse load of SSB with UDL. Collapse load of a simply supported beam with UDL is generally given as 8 MP upon L square. Collapse load of SSB with point load at the center, it would be 4 MP upon L. Fine. Next, similarly, SSB simply supported beam with point load anywhere. Simply supported beam with point load anywhere. Simply supported beam with point load anywhere. What we can say here is an SSB point load anywhere on the beam, not exactly at the center, it can be anywhere. Fine. Let us say this distance is A, this distance is B, this distance is L, this is W. Fine. Same thing, one plastic hinge has to be formed because this is the stable structure, and that plastic hinge will form exactly under the load because this is where bending moment is maximum also. This is MP, this is also MP, and if this would be alpha, here theta will not be same, so I'll take this as alpha, this is beta, this is A alpha, B beta. Fine. If this is B, this is beta, this is B beta, if this is A, this is alpha, this is A alpha, we can write down A alpha equals to B beta. Fine. We can write down A alpha equals to B beta, and MP, this is alpha, this is beta. So if you apply principle of virtual work, applying principle of virtual work, what we can write over here is applying principle of virtual work, applying principle of virtual work, external work done equals to internal work done, external work done equals to internal work done, external work done equals to internal work done. What you can write over here is W multiplied with A alpha, W multiplied with load multiplied with A alpha equals to MP times alpha plus beta, MP times alpha plus beta, right? So W times A alpha equals to MP times alpha plus beta, so that is alpha plus A alpha by B. So this is MP times B plus A multiplied with alpha upon B, that equal to W times A alpha. W equals to MP times B plus A upon AB. So collapse load A plus B equals to L, that is MPL upon AB. This is the simple collapse load. Collapse load. Collapse load for an SSB with point load anywhere. Collapse load for simply supported beam with point load anywhere. Collapse load of simply supported beam with point load at center is 4 MP upon L. Collapse load for a simply supported beam with UDL is 8 MP upon L square. I have given you the proofs. So for any type of beam, for any type of structure, you have to try to find out something like this. Fine. So with this, I'll close this session. In the next session, we'll see how to find out the collapse loads for fixed beams, for fixed beams and propped cantilever beams, and some of the different types of beams. Okay. Our next one is quick revision series. This is quick revision of steel structure, right? Quick revision of steel structures. Quick revision of steel structures. So we'll be discussing what are the important topics over here. What is that you have to remember? All those concepts that I have discussed in PDGD courses, each and every chapter in a different format I have discussed, right? So now we'll be dealing all those things. All the things we'll be revising in a matter of 4 to 5 hours. I'll try to complete everything. What are the major concepts that you have to remember, major formulas, and how to derive those things in a faster format, and what are the important points that you have to remember, and all those things. Fine. Let me check whether mic is on or not. Yeah, mic is on. So this, you can take this as the short notes, or whenever you have time, you can open it and just watch these videos, so that it will be helpful to remember the important concepts and important formulas. Okay. So whenever I start steel structures, the first thing I'll say is plastic analysis. That is a major one that you have to remember, right? So plastic analysis. In this video, we'll be doing the quick revision of plastic analysis. So in plastic analysis, whenever we start plastic analysis, first thing you have to remember is assumptions. Assumptions in the plastic analysis, right? So assumptions in plastic analysis. In assumptions of plastic analysis, the very first point is plane section remains plane before and after bending. The first point is plane section remains plane section remains plane plane section remains plane before and after bending, right? Plane section remains plane before and after bending. This assumption is also called as Bernoulli's assumption, and according to this assumption, strain variation is linear, right? According to this assumption, strain variation, according to this assumption, strain variation is linear. Okay, so that is what you have to remember. That means if at all I have to take a beam cross section. This is the cross section of the beam I am showing. Okay, variation of strain along the depth, variation of the strain along the depth this is variation of strain variation is linear. Fine. So if strain variation is linear, then you can apply the Bernoulli's, you can apply the moment formula. That means m by I equals to f by y equals to E upon R. Fine. So in order to show that this formula is applicable, we are showing it like this. Strain variation is linear, not stress variation. Strain variation is linear. This is your first assumption. Next assumption was beam is symmetrical. Beam is symmetrical with respect to the plane of loading. So that there will be only bending moments. So that there will be only bending moments. Without any twisting moment. So that there will be only bending moments without any twisting moment. Fine. So what I am saying is beam should be symmetrical with respect to loading. Whenever you are applying the loading, loading should be exactly at the center of the longitudinal axis. If I take this as the longitudinal axis, loading should be exactly at the center. Fine. So if at all there should be only bending moment. There should not be any twisting moment. Right. See, that means, let us say this is elevated view, or you are seeing from the front. This is the beam. From the top, if you see, if I show you the top view, if I have to show you the top view, it's like you will be applying W1, W2 here. Let us say if there is W1 and W2 here, or W1 and W2 here. W2, W1. Fine. I'm showing you the top view. This is top view. Top view. Fine. So if it is applied exactly on the longitudinal axis, something like this, if it is exactly applying over there, both are on the same line, then here there will be only bending moment. There will be only bending moment. So you will be designing only for the bending stresses. You will not be designing for any other things. Okay, and here there will be twisting moment as well as bending moment. Twisting moment and also twisting moment and also bending moment. Twisting moment and also bending moment. Fine. So it will try to twist something like this. Because of this load it tries to twist like this. Because of this load it tries to twist like this. So there will be bending as well as twisting. In order to avoid that, what I am saying is beam should be symmetrical with respect to loading. There should be only bending moment. There should not be any twisting moment. Fine. So this is your next point. This is your next point. Loading should be beam is symmetrical with respect to the loading, so that there will be only bending moments without any twisting moment. Okay. So this is the other point. Next, similarly, other basic things are axial deformations and shear deformations are neglected. Axial and shear deformations. Axial and shear deformations are neglected. Axial and shear deformations are neglected. And Young's modulus E is same in tension and compression. Young's modulus is same in tension and compression. So these are some of the basic things. E value is same, is tension and compression. Generally for steel structures, E value would be 2.1 into 10 to the power of 5 Newton per mm square, right? E for steel equals to 2 into 10 to the power of 5 megapascals or Newton per mm square. This is one of the things. So axial and shear deformations are neglected. Okay, so we have seen Young's modulus is same in tension and compression. Next point is, this is also one of the important point, stress-strain relationship. Stress-strain relationship. Stress-strain relationship for elastic analysis. Stress-strain relationship for elastic analysis is assumed to be bilinear. Stress-strain relationship for elastic analysis is assumed to be bilinear. Stress-strain relationship for elastic analysis is assumed to be bilinear. Fine. So what exactly it means is, generally stress-strain analysis, stress-strain curve for elastic analysis. Stress versus strain. This is stress-strain curve for elastic analysis. Fine. So there will be proportionality limit, there will be elastic limit, there is upper yield point, there is lower yield point, and this one is plastic zone. This is ultimate point, breaking point. Strain hardening, EF is strain hardening zone and FG is strain softening zone. Fine. This is stress strain curve for mild steel for elastic analysis. Idealized form of stress strain curve for plastic analysis would be, something like this. Fine. So this would be your yield stress. After that, even though if you increase the strain, that means up to certain point, with increase in the strain, stress will increase. That means Hooke's law is applicable. Stress is directly proportional to strain up to certain point, let us say yield strain. And after that, even though if you increase the strain, stress will remain constant. This is idealized stress strain curve for plastic analysis. Idealized stress strain curve for plastic analysis. Idealized stress strain curve for plastic analysis. This is stress strain curve for elastic analysis, and this is idealized stress strain curve for plastic analysis. Okay, so this is what I am trying to say, that stress strain relationship for plastic analysis. Please change it over here. Stress strain relationship for plastic analysis is assumed to be bilinear. Okay, fine. Now accordingly, since stress strain relationship is bilinear, now see the stress variation over here. Stress variation, that is very much important. Here strain variation is always linear, whether it is for plastic analysis or elastic analysis, strain variation is linear, but stress variation will change. Fine. So what happens is, because of the strain variation, strain is directly proportional to the stress. So what I can write over here is, this is your stress variation. Fine. Strain is directly proportional to stress. This is your stress variation. It can be some F. Okay. Top members will be generally in compression, bottom members will be generally in tension because of application of load. In general, I am talking over here. Fine. Next, if you further increase the load, what happens is the beam will yield. So at the point of yielding, yield stress will develop. This is Fy, this is also Fy. At the point of yielding, yield stress will develop. Fine. Next one is, so with further increase in the loading, from here to there, if you are increasing the loading, what happens is stress is Fy, so it has reached its maximum. With increase in the loading, strain will increase. So what happens is, each and every fiber below this will start reaching up to Fy. That means here, if you see, this is stress variation. All these things are stress variation only. Fine. So this is also stress variation. All three things are stress variation. Okay, stress variations only. So here, because of some loading, let us say 10 kilonewton load, this is the stress variation, and 20 kilonewton load, this is the stress variation. So this is the stress variation. At the top and bottom fibers, it has reached to its maximum Fy, and after that, with further increase in the loading, with further increase in the loading, so the stress variation will be something like this. That means each and every fiber tries to reach up to the plastic moment capacity. This is stress variation at plastic moment capacity. Fine. So this one is simply what I call it as stress variation at plastic moment capacity, right? Stress variation at plastic moment. After that, after plastic moment, that means if it reaches to its maximum, then it is converted into the hinges, right? That means failure. Once it reaches up to here, it has reached its maximum strength. That means failure has occurred. Here it is stress variation at yield moment. This is stress variation at yield moment. Stress variation at yield moment, stress variation at plastic moment, stress variation at yield moment, and this is stress variation at working moment. Stress variation at working moment. Stress variation at working moment, stress variation at yield moment, stress variation at plastic moment. Fine. So these are the points that you have to generally remember. Strain variation is linear here. So since stress is directly proportional to strain, this is the stress variation. Fine. At some working moment, and once it yielded, this is stress variation at yield moment, and this is stress variation at plastic moment. Based on stress variation, we'll try to find out what is the load carrying capacity. Fine. So, or moment carrying capacity. Generally, what is the formula that is applicable? M by I equals to F by Y equals to E upon R. Fine. So, if you ask for working moment, M upon I equals to F upon Y. So M equals to F multiplied with I upon Y. So M equals to F multiplied with Z, where Z is the section modulus. Z equals to I by Y, that is section modulus. Z is called section modulus. Z is called section modulus. This is working moment. Fine. And yield moment. If I have to talk about yield moment, M by I equals to Fy upon Y. So My equals to Fy multiplied with I by Y. So that is Fy multiplied with Z. This is yield moment. Fine. So up to working moment and yield moment, you can use this flexor formula M by I equals to F by Y equals to E upon R. If you have to find out plastic moment, you can't use this. You can't use that because stress variation is not linear. Only strain variation is linear, and stress variation is something like this, right? Fy, everywhere it is Fy. Stress variation is something like this, Fy and Fy. I'm not giving you the proof. I'm just giving you the idea of how to find out the things, compression force, tension force, and all those things. Directly, I think you will be knowing the formula, that is plastic moment equals to Fy multiplied with Zp. So if this is your stress variation, then here there will be compression, here there will be tension, right? This is compression, this is tension, this one is Fy, this is also Fy, this is B, depth is B, and this axis is called as plastic neutral axis. Plastic neutral axis is also called as equal area axis because this divides the area into two equal halves. So you can take this as the note. Plastic neutral axis is also called as equal area axis. Plastic. You have to remember these points, right? While reading, you might have seen this. Plastic neutral axis is also called as equal area axis. plastic neutral axis is also called as equal area axis, and generally neutral axis would be centroidal axis, right? So I'll call that as normal neutral axis as elastic neutral axis. Elastic neutral axis is elastic neutral axis is centroidal axis. Elastic neutral axis is centroidal axis. Fine. So elastic neutral axis is centroidal axis, and for symmetrical sections, plastic neutral axis and elastic neutral axis coincide with each other. For symmetrical sections, plastic neutral axis and elastic neutral axis coincides with each other. Fine. Anyway, okay. So this member is in equilibrium. So since this member is in equilibrium, what we can write over here is summation of forces in x direction equals to 0. So compression would be equals to tensile force. Compressive force equals to tensile force. And if I take this as some x, this distance as some x, this distance would be d minus x. If this is x, this would be d minus x. This would be d minus x. So if you want to find out compression force, that is stress multiplied with area. Average stress is Fy only. Fy multiplied with area is B multiplied with x. This is the stress variation, right? Stress variation at plastic moment capacity. Stress variation at plastic moment. Stress variation at plastic moment. So compressive force, if you want, that is area multiplied with average stress. So C equals to B multiplied with x multiplied with Fy, and T. T would be equals to B multiplied with D minus x multiplied with Fy, right? So T equals to B multiplied with D minus x multiplied with Fy. So Fy, B, B. So x would be equals to D by 2. So you can see that this axis, that is depth of plastic neutral axis is d by 2 is what you got, that divides the area into two equal halves. Not only here, anywhere plastic neutral axis divides the whole area into two equal halves. Fine. So if you want to find out plastic moment, this is like a equal and opposite force which are acting at a distance, equal and opposite force which are acting at a distance. So if I can call this as lever arm. Find the distance between two forces, I can call that as lever arm. So moment carrying capacity would be equals to forces multiplied with distance between the forces, right? Forces multiplied with distance between the forces. So MP, plastic moment, MP would be equals to C multiplied with lever arm, or T multiplied with lever arm. C multiplied with lever arm or T multiplied with lever arm. How you are going to find out C multiplied with lever arm or T multiplied with lever arm? Let us say centroid of this area from plastic neutral axis is y1 and centroid of this area from elastic neutral axis, because forces will act exactly at the centroid. This is y1 and y2. Centroid of this bottom area from plastic neutral axis is y2. Centroid of this top area from plastic neutral axis is y1. If I say that, then lever arm would be equals to y1 plus y2. So this is equals to y1 plus y2. So C multiplied with the lever arm or T multiplied with the lever arm. So what is the value of C? C equals to B multiplied with or I can also write this as A by 2. Area is A by 2 multiplied with Fy. This is C force multiplied with lever arm is Y1 plus Y2. Right? Half of the area. Area above the plastic neutral axis is half of the area. Area below the plastic neutral axis is another half. So A by 2 into Fy multiplied with Y1 plus Y2. So how I can write this as Fy multiplied with A by 2 multiplied with Y1 plus Y2. A by 2 multiplied with Y1 plus Y2. So I can also write this as Fy multiplied with Zp. Fy multiplied with Zp, where Zp is the plastic section modulus. Zp equals to plastic section modulus. This is called as plastic section modulus. Plastic section modulus, that is further equals to A by 2 multiplied with Y1 plus Y2. A by 2 multiplied with Y1 plus Y2. This is plastic moment. Fine. So elastic moment or yield moment is generally given as yield moment equals to yield moment My equals to Fy multiplied with Z, whereas plastic moment Mp equals to Fy multiplied with Zp. Plastic moment Mp equals to Fy multiplied with Zp, and yield moment My equals to Fy multiplied with Z. And working moment is generally given where Z equals to elastic section modulus or section modulus. Elastic section modulus or section modulus or section modulus, and that is generally given as I upon Y. You have to calculate moment of inertia about the centroid, and Y is the distance from the neutral axis to the longest fiber, not longest fiber, farthest fiber. Okay. So this is Z, and Zp would be equals to A by 2 multiplied with Y1 plus Y2. So this is how you will try to find out plastic moment and yield moment, and working moment is generally given as Fy multiplied with Z. Working moment equals to F multiplied with Z. Yield moment is Fy multiplied with Z. Plastic moment is Fy multiplied with Zp, and working moment is F multiplied with Z. Zp equals to A by 2 multiplied with Y1 plus Y2. So these are the points that you have to remember regarding plastic moment capacity. Fine. Now, generally, if they ask what is the relationship between moment and curvature, relationship between moment and curvature would be something like this. All these points in detail were discussed in the class. Here we are just revising it quickly. Okay, so just don't expect all proofs and all these things. Fine. Curvature 1 upon r at curvature equals to infinity, moment equals to mp. Fine. So what you can write over here is m by I equals to f upon y equals to e by r. So m equals to ei upon r. What I can write is m is proportional to 1 by r. With increase in the curvature, moment keeps on increasing at plastic stage. This is at plastic stage. At plastic stage, that means at failure stage, at plastic stage or failure stage, moment equals to mp. Curvature would be infinity. At plastic stage, what I can write over here is at plastic stage m equals to mp, and curvature is infinity. M equals to mp and curvature is infinite. Not radius of curvature. Curvature is infinite and m equals to mp. Fine. And m equals to ei upon r. This is your another point. Fine. Moment versus curvature. So m equals to mp and curvature is infinite. Fine. So this is one of the relationship. Next, one of the foremost important thing is shape factor. Shape factor. So shape factor SF is generally given as ratio of plastic moment to yield moment. It is given as plastic moment, ratio of plastic moment to yield moment. Ratio of plastic moment to yield moment, shape factor equals to MP upon My. So MP equals to Fy multiplied with Zp upon Fy multiplied with Z. So shape factor equals to Zp upon Z. Fine. Shape factor equals to Zp upon Z, where Zp is the plastic section modulus and Z is the elastic section modulus. Zp equals to plastic section modulus, plastic section modulus, and this value is generally given as A by 2 multiplied with Y1 plus Y2, and Z is the elastic section modulus, elastic section modulus, that equals to I upon Y, So shape factor equals to Zp upon Z. Zp is plastic section modulus, Z is elastic section modulus, that is I upon Y. So once this point is completed, so what does shape factor exactly represent? Shape factor exactly represents the reserved strength of the material. Fine. So shape factor, it represents the reserved strength of the material, right? it represents reserved strength. It represents reserved strength of the material. So higher is the shape factor. What exactly means is, if shape factor is more, higher is the shape factor, more is the amount of reserved strength or unused strength. So that means material is useless. Generally you will load up to My only, you will not load up to MP. This is always greater than or equal to greater than 1. Okay, fine. So first there will be yielding and finally there will be failure, right? So it represents reserved strength or unused strength. So unused strength, that means that huge, if shape factor is more, high amount of unused strength in your body, there is high amount of unused strength. That means your body is more useless. The idea is what, whenever you are designing something, your whole body, let us say if your body is designed, each and every part is to be utilized to the maximum, then only it would be more useful section, right? If there is huge amount of fat somewhere which is not used properly, this is not good for you, as well as you are not useful for much, you are not useful for many things. Okay, so that is the idea. It represents a reserved strength of the material. Okay, so shape factor, that is plastic moment upon yield moment, what does it represents? It represents reserved strength of the material, and generally shape factor should be more than 1. Shape factor should be more than 1. So I'll just give a small example for rectangular section of dimensions B by D, how to find out the shape factor, right? So if let us say this is B, the depth is D, the depth of plastic neutral axis, since member is symmetrical, it would be equal to elastic neutral axis, or it coincides with centroidal axis. Centroid would be at a distance of D by 2, D upon 2. Fine. Centroid will be at a distance of D upon 2, and this is also D upon 2. B, D by 2. B, D upon 2 and D upon 2. This is plastic neutral axis, and stress variation would be, what is the stress variation? Stress variation will be uniform, right? Stress variation is uniform. So your idea is what? Idea is to find out shape factor. Shape factor equals to Zp upon Z. Shape factor equals to Zp upon Z. Zp equals to A by 2 multiplied with y1 plus y2. Fine. What is total area? Total area is b into d upon 2 y1 plus y2, right? So y1 is centroidal distance of this area from the neutral axis is, this is y1, and centroidal distance of this area from neutral axis is y2. So what would be the centroidal distance? If it is d by 2, centroid will be exactly at the half. This is at d by 4. This is also at d upon 4. This is a simple problem. I am not discussing each and everything in detail. In examination, in the PDGD courses, it was discussed in detail. But for all the other things, you have to derive something like this. Okay, I am just giving a basic example. y1 and y2, that is d upon 4 plus d by 4. d by 4 plus d by 4. So this is equals to bd by 2 multiplied with d upon 2, that is bd square upon 4. This is zp, and z equals to I upon y. I equals to bd cube upon 12 upon y is d by 2. So that equals to bd square upon 6. Z equals to bd square upon 6, and shape factor equals to zp upon z, that is bd square upon 4 upon bd square upon 6, that is 6 upon 4, that equals to 3 by 2. Shape factor equals to 3 by 2, that is 1.5. So for rectangular section, shape factor is 1.5. This is how you will try to find out. So for different sections, what are the shape factors? If I have to go in the ascending order, for I section, first one is for I section. For I section, shape factor is very less. I mean less in the sense, the minimum is generally for I section. That is the reason we generally prefer I section for all the things. Okay, so shape factor is generally in the range of 1.1 to 1.2. We will take 1.12. Next, for a hollow tube. For a hollow tube, shape factor equals to 1.27. For a rectangle or square, rectangular square, shape factor equals to 1.5, and for head sections, shape factor equals to, for head sections, shape factor equals to 1.5. For head sections also, shape factor equals to 1.5. For a solid circular section, this is solid circular section, this is a thin tube. Okay, shape factor equals to 1.7. And for diamond section, shape factor equals to 2. For diamond section, shape factor equals to 2, and for triangular section, shape factor equals to 2.34. You have to remember these values. If you remember, your problems will be solved easily. But in engineering services, I think remembrance is important. In gate, concept is important, because they will give different types of structures, and accordingly you have to find out. Fine. So concept is very simple. Shape factor, if you want to find out, Zp upon Z, Zp equals to a by 2 into y1 plus y2, and Z equals to I upon y. Z equals to I upon y. Fine. So you have to just find out centroidal from plastic neutral axis, not from elastic neutral axis. For symmetrical sections, plastic neutral axis and elastic neutral axis coincides. If it is not symmetrical, then it would be totally different. Fine. So suppose if I have to take a triangular section is not symmetrical. Fine. Generally, plastic neutral axis will be at a distance of h upon root 2. H by root 2. If I total depth is h, So plastic neutral axis will be at a distance of h upon root 2. Fine. And elastic neutral axis will be at a depth of 2h by 3. Fine. That would be h upon 1.5. This is h upon 1.414. Elastic neutral axis will be at a depth of 2h by 3. Elastic neutral axis will be at a depth of 2h by 3. This is elastic neutral axis, and plastic neutral axis will be at a depth of h upon root 2. Plastic neutral axis will be at a depth of h upon root 2, and elastic neutral axis will be at a depth of 2h upon 3. So elastic neutral axis and plastic neutral axis coincides only for symmetrical sections. It will not coincide for unsymmetrical section. At the same time, you should know how to find out the I value for different sections, and you should know how to find out the centroidal values for different sections. Then only you can easily find out ZP and you can find out Z. From that, shape factor is calculated. So I have just given you some of the basic assumptions and some idea of how to find out the shape factor. So shape factor indirectly represents what? It represents reserved strength or unused strength. Okay. Next one is load factor. Load factor. Load factor LF would be equals to, it is generally given as plastic moment upon working moment. Plastic moment upon working moment. Plastic moment upon working moment. Fine. So plastic moment is MP and working moment is M. Plastic moment upon working moment, plastic moment is MP upon M. That is Fy multiplied with Zp upon Fy, F multiplied with Z, not F multiplied with Z. So this I can also write it as Fy upon F multiplied with Zp upon Z. This is load factor, plastic moment upon working moment. Fine. This is in steel. In RCC, it would be ultimate stress upon working stress. Right. The same thing over here. So Fy upon F is generally given as factor of safety, and Zp upon Z is generally given as shape factor. Fine. So load factor equals to load factor LF is factor of safety multiplied with shape factor. You also have to remember these things. Fine. So this is how you'll try to, these are some of the basic minimum concepts that we'll see. The next one is how to find out the collapse load, that I'll discuss in the next video. These are the certain points that you have to remember. Okay. Fine. So next we'll see how to find out collapse load in beams. Next we'll see collapse load in the frames, and then we'll go for the bolts and bolted sections, and then we'll go for bolted and riveted sections. Next we'll go for welds. Next we'll go for tension members, compression members, beams. Fine. So this is how we'll be discussing the thing. Maximum in 4 to 5 hours I will try to complete the revision. Okay. Thank you.